Hello and welcome to the Calculus 1 course. This is intended to be a course where you can learn all of Calculus 1 in one video. So I'm glad that you're here and hope that you enjoy. So let's take a look at what is calculus. So calculus is the math that focuses on change. And that's one of the most important things to understand about calculus is that the math relates to stuff changing in a way. So some prerequisite knowledge. That with the content that's going to be covered, you're going to be expected to know is algebra and pre-calculus. So topics like real numbers, functions, like linear, quadratic, exponential, etc., as well as graphs and trigonometric functions. So if you're not familiar with a lot of these topics, then I would recommend trying to look up some other videos, trying to learn them yourself. But also at the same time, maybe with the way this course is being taught, maybe you might catch on to some of what this stuff is if you haven't learned it already. But if not, then that's what I would recommend doing before looking at this course. So all that being said, let's get started. And like I said before, I'm really glad that you're here and that you decided to take the time to come and watch this course. And I hope that this course is helpful to you. And if you're wanting to learn calculus or you're wanting to go back and relearn calculus because you may have forgot it after learning it a long time ago, or you're just wanting to learn another topic, then I'm glad that you're here and I hope that you enjoy. This is just some of the things you see associated with calculus, some little images, and by the end of this course, hopefully you'll understand what these mean. So let's take a look at the first topic. So I'm going to change pen colors here. And that topic is going to be rates of change. So the name speaks for itself. This topic talks about how something changes and quantifies it or gives it a value. So let's say we have a graph of x squared. So let's try to make just a mini graph here of x squared. So let's get our points 1, 2, 3, 4, 4, 1, 2, 1, 1, 2, and -1, -2. So these are the points, and then we'll draw the graph out. Well, try to reconnect those dots. Seems that my point disappeared. So let's say we have this graph and we wanted to know how long it takes to get from the point x equals 0.2 to x equals 1.5. So we can look at two rates of change to describe this. So the first one is the average rate of change. So the average rate of change is the average value to get to the point, otherwise known as the slope of the secant line. And if we were to go back up to our graph and graph this, let's see, we're going from 0.2 to 0.5. 0.2 is about here, or 1.5, excuse me, and 1.5 is about here. We would draw a line, maybe you can kind of make it out sort of like that. It goes between 0.2 and 1.5. So there's a formula that describes the average rate of change. And that formula is delta f over delta x equals f of x1 minus f of x naught over x1 minus x naught, where for this problem fx is x squared, x1 is 1.5, and x naught is 0.2. So this is an important formula to remember because it will come up in later sections that we will go over in Calculus 2. So if we were to plug in our values, we would have 1.5 squared minus 0.2 squared over 1.5 minus 0.2, and that gives us 1.7. And then the next one we have is the instantaneous rate of change. And this is the rate of change at a specific point, which for our case would be when x equals 0.2 or when x equals 1.5. So we can estimate this by using smaller intervals closer to the points. So we can do something like x equals, or x not equals 0.2. Sorry, let me erase this. And x1 0.201, and use the above formula, the one we use for the average rate of change, or we can use something we will learn later to find this, and that is derivatives. And another thing to understand is that the instantaneous rate of change is the slope of a tangent line. And that's an important thing to remember when understanding the difference between a secant and a tangent line. So for the instantaneous rate of change, the secant line went through 2 points that were on the graph. And then for the tangent line, only goes through 1 point of the graph. Well, see if I can draw this right. So that's the big difference between a secant and a tangent line. So, yep. Okay, let's move on to the next topic. Let's change colors here, and we will look at, let's go with red. We will look at limits. So, the definition of a limit let me close this out. Limit describes how a function behaves as it approaches a value. So the notation for limits Thus, let fx be the function, c be the open interval x is defined on, and L be the limit. So we write it as we put LIM, an abbreviation for limit, as x approaches c of our function f of x equals L. So an example, find the limit as x approaches 0 of 1 over x. So since 1 over 0 is undefined, we can look at it graphically. So this is kind of the general graph of 1 over x. So label my axes. We have two limits as x approaches 0. We'll put a plus sign to say it approaches from the right and as x equals 0 with a superscript minus, which means it approaches from the left. So therefore, our limits are the limit as x approaches 0 from the right is infinity, and the limit as x approaches 0 from the left side is negative infinity. And how we can determine that is we just need to look at it graphically, and you'll see on the right side of the graph that it's going to constantly keep going up. It's never going to touch 0 because it's undefined there, so it's approaching infinity. And the same can be said on the left side. It's never going to touch 0, and it's going to keep approaching negative infinity. So some limits can be solved algebraically. So an example is, let's look at the limit as x approaches 2 of x squared minus 3x plus 2 all over x squared plus x minus 6. So if we plug it in, we 2 squared minus 3 times 2 plus 2 all over 2 squared plus 2 minus 6, which equals 4 minus 6 plus 2 over 4 plus 2 minus 6 equals 0 over 0. So this is known as indeterminate form. Because we have 0 divided by 0. And indeterminate form is also when we have infinity over infinity, 0 times infinity, or infinity minus infinity. So instead, let's factor out the numerator and denominator. So we have x squared minus 3x plus 2 all over x squared plus x minus 6. And that gives us, we can factor out x minus 2, x minus 1 all over x minus 2, and x plus 3. And then the x minus 2's will cancel out, and that gives us x minus 1 over x minus 3. So now we have the limit as x approaches 2 of x minus 1 over x minus 3, which equals 2 minus 1 over 2 minus 3. Excuse me, it's supposed to be plus 3. Equals 1 over 5. So by factoring out and canceling some terms, we were able to find the limit of this function. So now, for limits involving trigonometric identities, there are two important formulas to remember. And that is one theorem, which is the limit as theta approaches 0 of sine theta over theta equals 1, and the limit as theta approaches 0 of 1 minus cosine theta over theta equals 0. And basically with these formulas, why you want to remember them is that when you have the limit with a trig involved, you will more likely than not be able to modify it in some way where you can get it in this form, and then you can eliminate these terms by substituting 1 or 0 depending on which one it is. And there's also another theorem to know that the cosine of theta is less than or equal to sine of theta over theta, which is less than or equal to 1 for negative pi over 2 is less than theta is less than pi over 2, where theta is not equal to 0. So that's pretty much all there is to understand about limits with trig identities. Now limits can be evaluated at infinity and negative infinity. So this gives us a definition of the limit of an exponential function and that limit is that the limit as x approaches infinity of e raised to the x is infinity, and limit as x approaches negative infinity of e of x equals 0. And probably the easiest way to understand where this limit comes from is to simply look at the graph of e of x. And this is just generally the graph of e of x. And you'll see that as e of x approaches positive infinity, as it keeps going on, it's approaching infinity because it keeps going up. And then as it approaches negative infinity, as it keeps going on the left side of the graph, it approaches 0, but it's never going to touch it pretty much. Okay, so now let's change colors. We have a new topic. We're going to look at basic limit laws. So there are a few limit laws to understand and memorize, and we have a whole table of these laws. So I'm going to copy and paste it from my notes that I'm using to lecture you from on here, just to save me a ton of writing, and then we'll just look at the table and I'll talk about what they are. Okay, so I have copied the table over, so let's take a look at the table and see what we have here. So the basic statement for this table, if we have the limit as x approaches c of f of x and the limit as x approaches c of g of x, if they both exist, then we have a sum law. So the sum of f of x and g of x as x approaches c exist, then we can just split them up into their individual sums, x approaches c of f of x and x approaches c of g of x. Then we have constant multiple law, which is for any number k, the limit as x approaches c of k f of x exists, and then the limit as x approaches c k f of x, so we can just move that constant k on the outside and multiply it by the limit. Then the product law says that as the limit as x approaches c of f of x and g of x exist, then we can basically split them up and multiply them individually for both functions. Then the quotient law, if the limit as x approaches c of g of x is not equal to 0 and the limit as x approaches c of f of x divided by g of x exist, then what we can do is we can just look at the limit of the individual functions on the denominator and the numerator. And then we have the power and roots, and this theorem or this law states that if n is a positive integer, then the limit as x approaches c of f of x raised to the n is simply the limit itself raised to the power of n. And also if we have an nth root of f of x as x approaches c, then we can just take the nth root of that limit and not do the nth root of the function. And then in the second limit, if we assume that the limit as x approaches c of f of x is greater than or equal to 0, and if n is even, and then if p and q are integers where q does not equal to 0, then the limit as x approaches c of f of x raised to the p of q over q exists. And the limit as x approaches c of f of x raised to the pq, where we can just find the limit, then raise the power of that. And then we can assume that the limit as x approaches c of f of x is greater than or equal to 0 if q is even. Then we have the limit as x approaches c of f of x is not equal to 0 if p and q is less than 0. And also from these laws, we can find that the limit as x approaches c of x raised to the pq, well, it's just simply c raised to the pq. So that's pretty much all there is for the basic limit laws. It's just a giant table of values to recognize. So now we'll move on to the next topic. We will be looking at continuity and the Squeeze Theorem. So a limit is that it is continuous has no breaks or interruptions. So the definition, or we're going to look at a definition, if a function f of x is defined on an open interval containing x equals c, f is continuous at x equals c if the limit as x approaches c of f of x equals f of c. And if the limit does not exist, sometimes written in shorthand notation as D and E, or is not equal to f of x, then f of x has a discontinuity. At x equals c. So there are some types of discontinuities that we're going to look at. And those continuities are removable. So here's kind of a little graphical way to look at what a removable discontinuity is. So let's say we have 1 and then 4. We have this point here, and then we have another point at 8. But our graph is kind of like this. Well, then the point can be redefined at this discontinuity. We can just redefine the point that we have here at 1, 8 to be part of the rest of the function for this type of discontinuity. And then we have a jump discontinuity. Let me put a little underline all these to know when we look at the next one. So for a jump discontinuity, we'll look at this graphically. Let's say we have this going like this. And then we have another one goes like this. So for these discontinuities, we can define a one-sided continuity, and that is either a left continuous at x equals c if the limit as x approaches c of f of x. Oh yeah, and this is going to be from the left side equals fc, and then we have right continuous at x equals c if the limit as x approaches c from the right side of f of x equals f of c. So yeah, that's essentially what a jump discontinuity is. And usually this is like related to something like a piecewise function where you have different functions that are on different intervals. And then we have an infinite discontinuity. And an infinite discontinuity, say we have a graph like this and one like this, and then we have this asymptote that's between them. So this one is kind of like 1 over x. You would generally just have to look at it and try to figure out the limit graphically, unless maybe there's some way you can algebraically manipulate it to find the limit. And those are the 3 types of discontinuities: removable, jump, and infinite. Now let's look at the Squeeze theorem. So the Squeeze theorem, let's consider a function f of x that is trapped between 2 functions. So let's draw this out. give it a little visual. So we have our point C, and we'll have a graph that's sort of like this. And one maybe that goes somewhat like this. And then another one that goes something like that. Then we'll define this top one as y equals u of x. This one is y equals f of x. And then the bottom one is y equals L of x. So we have L of x is less than or equal to f of x is less than or equal to u of x for all imaginary numbers I, or imaginary numbers x. So now let's assume that for x does not equal c, which in some open interval containing c, that L of x is less than or equal to f of x, which is less than or equal to u of x, and the limit as x approaches c of L of x equals the limit as x approaches c of u of x equals L. So then we have the limit as x approaches c of f of x exists, and the limit as x approaches c of f of x equals L. So this is basically the entire definition of the squeeze theorem. So if we were to do it with this graph that we have right here, we would have the graphs would become something like that. Then our middle graph would still remain the same. It would go through this point. And this one would go something like that. We still have our three functions. So we have f is squeeze by L and U at x equals c. And that's pretty much all there is to the squeeze theorem. So now, change pen colors here. We are going to look at the intermediate value theorem. Value theorem. So the theorem is if f is continuous on a closed interval AB, then for every value m between FA and FB, there exists at least one value C that is in AB such that f of C equals m. So basically, if we would put this in simpler terms, a continuous function cannot skip values. And then there's a corollary to this. And that is if f is continuous on the interval AB and if f of A and f of B are non-zero and have opposite signs, then f has a 0 in the interval AB. So an example of this, let's look at for f of x equals cosine x. We have cosine of 0 equals 1, while cosine of pi equals -1. So therefore, a value of C must exist such that cosine of C equals 0, and of course, if you were to figure this out, pi halves is the answer. And you can just simply look at the graph of cosine of x to understand how this works. So we have 1 and -1, and this is 0, and then let's call this pi. So cosine is going to go something like that. Let's try to make it look a little more. There we go. Of course, it goes back this way too. So you can see that we have our point 0, 1 here. Then we have our point pi -1. So the intermediate value theorem basically is telling us that we must have a 0 because we have values between 1 and -1. And that's pretty much all there is to understand about the intermediate value theorem. And the general intermediate value theorem is different because it doesn't focus just on zeros. It just says, like, say we change this to 5 and 2. Well, we can, with the intermediate value theorem, tells us that we must have a value of 3 somewhere in there. All right, let's look at the last topic for limits, and that is going to be the formal definition of a limit. So, previously, the definition of a limit was the limit as x approaches c of f of x equals L with the condition as the absolute value of f of x approaches L becomes arbitrarily small as x approaches c. So through further studying a more rigorous and precise definition of a limit has been defined, and this is the definition. The definition is, suppose f of x is defined for all x in an open interval containing c, but not necessarily at x equals c. So then we have the limit of f of x equals L as x approaches c. And try to keep that under the limit. If for all epsilon greater than 0, there exists delta greater than 0 such that if 0 is less than x minus c, or the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. So this definition lets us know how close is sufficiently close for finding a limit. Now we will look at some problems about rates of changes and limits. So the first problem we have is a pendulum has a period t, which is represented by t equals 3/2 the square root of L, where L is the pendulum's length. We are asked to find the average rate of change over lengths 1 to 4, or the interval 1 to 4, and then estimate the instantaneous rate of change when L equals 5 meters, and then what are the units for the rate of change if we let L be meters and T be seconds. All right, let's take a look at this problem. So for part A, we are going to use delta T over delta L, because if you remember, for the average rate of change, the formula was delta F over delta X, where F is the formula and X is the variable. So we will have 3/2 square root of 4 minus 3/2 square root of 1 over 4 minus 1. And that will be equal to 3/2 times 2 minus 3/2 times 1 over 3. And that is equal to 6/2 minus 3/2 over 3, which is equal to 3/2 minus 3, which equals 1/2. And that's our average rate of change. Now for part B, let's use the interval 5 to 5.1, and then 5 to 5.01. Then the interval 5 to 5.001, and 5 to 5.0001 to estimate. So now we will use the same formula again. That's equal to 3/2 square root of 5.1 minus 3/2 square root of 5 over 5.1 minus 5. And that is equal to 0.33375. And then similarly, we will do T of 5.01 minus T of 5 over 5.01 minus 5. And then I'm not going to write it all out. I'm just going to go on and give the answer for this: 3.35243. Then we'll do the same for the other intervals, and we get 0.335393. And then we get 0.335409. So by using a smaller interval as we approach 5, we can see what the value is approaching to, and it looks like we're getting about 0.3354. So therefore, the instantaneous rate of change is about 0.3354. Then for part C, our rate of change is delta T over delta L, which is going off the formula delta F delta X. So seconds per meter is the units. You just simply divide the units or substitute the units into the fraction, and these are our units for the rate of change. All right, problem 2. We are asked to evaluate the following using the basic limit laws. So we have the limit as x approaches 2 of 7x to the negative third, and then the limit as t approaches 9 of 5t times 2t plus 5 over t plus 1, and then the limit as z approaches 3 of the square root of 27z. All right, so part A, we are going to use constant, multiple, and power laws. So let's start by factoring out the constant. 7 times the limit as x approaches 2 of x. And then we will take out the negative 3 and multiply by the entire limit. So that gives us 7 times 2 to the negative third, or we can rewrite this as 7 over 1 times 2 to the third, which is 7 times 1 over 8, which is 7 eighths. And then for part B, we will use the product and quotient laws, and that will give us the limit as t approaches 9 of 5t times the limit as t approaches 9 of 2t plus 5 over limit as t approaches 9 of t plus 1, and that will give us 5 times 9 times, let's put this in parentheses, times 2 times 9 plus 5 all over 9 plus 1, and then that will come out to 45 plus 18 plus 5 over 10, which is 45 times 23 over 10. Then we can simplify this further by factoring out a 5 from these, so that leaves us with 9 and 2. And that gives us 207 over 2. Now, for part C, we will use the root law and rewrite it as the limit as z approaches 3 of 27z all under the square root. So that's square root of 27 times 3, which is the square root of 81, which is 9. Or, well, technically plus or minus 9. Yeah, there we go. All right, that's it for problem 2. We just use the basic limit laws that we mentioned in the lecture to find all these limits. All right, for problem 3, we are given the piecewise function x cubed, where x is less than -2, and 7x, where x is greater than or equal to -2. So we are asked to compute the right and left-hand limits at x equals -2 and determine if f is left continuous, right continuous, or continuous at x equals -2. All right. So the left hand limit, let me try to rewrite this where it's a little clearer, is going to be limit as x approaches -2 from the left side. We'll indicate that with the negative by x cubed. So x is -2 cubed, which is -8. Then the right hand limit is going to be the limit as x approaches -2 from the right side or the positive side of 7x. And that's going to be 7 -2, which is -14. And then notice in the piecewise function that x cubed is strictly less than -2. So since x cubed does not include -2, let's write it as f x is right continuous. Because since we include our point -2 in the interval for 7x, then it is right continuous. All right, that's it for problem 3. Now for problem 4, we are asked to calculate the limit as h approaches 0 of h plus a squared minus a squared, all divided by h, where a is a constant. All right. Solution to this. We will use algebra to rewrite h plus a squared minus a squared over h. So let's FOIL h plus a squared, and that's h plus a times h plus a, and that gives us h squared plus 2ah plus a squared. So now we have h squared plus 2ah plus a squared minus a squared over h. So these cancel, and then we can write that as h squared plus 2ah over h. And then let's factor out an h on the top. So we have h plus 2a over h. Those cancel, and that gives us h plus 2a. So therefore, the limit as h approaches 0 of h plus a squared minus a squared over h equals the limit as h approaches 0 of h plus 2a, which is 2a. And that is it for problem 4. We just used algebra to rearrange or rewrite the fraction, and by doing so we were able to evaluate the limit, because if we plugged in the limit to the base equation, we would have had a division by 0, which we would have not been able to find it that way. Alright, for problem 5, we are asked to evaluate the limit as t approaches 0 from the right side of the square root of t times e raised to the cosine of pi over t using the Squeeze theorem. Okay, so the solution, we need to look at all three functions to determine the graph behavior. So the cosine of pi over t, notice that this one alternates between -1 and 1, because that is cosine's behavior. So we can rewrite this as e to the -1, which is less than or equal to e to the cosine of pi over t, which is less than or equal to e, because cosine alternates between -1 and 1, so we can just plug that in directly to e, and those will be our bounds for that graph. So now we can distribute the square root of t, and that will give us e to the -1 square root of t, which is less than or equal to square root of t, e cosine pi over t, which is less than or equal to e square root of t. So now let's look at both bounds and their limits. And we have the limit as x approaches 0 from the right side be -1 square root of t, which is equal to e -1 square root of 0, which is e -1 0, which is 0. And then for e square root of t, we also have e square root of 0, which is e times 0, which is 0. So therefore, using the Squeeze theorem, we have the limit as x approaches 0 from the right-hand side, square root of x e cosine, excuse me, this is supposed to be t, cosine pi over t equals 0. And yeah, that's how this problem worked, by looking at the bounds on the left and the right functions for e of -1 of square root of t and e square root of t, because e cosine pi of t is squeezed between them. we're able to figure out what the limit is. Now for problem 6. We are asked to evaluate the limit as z approaches infinity of secant 4z to the fourth times this fraction e z to the seventh, or e raised to z to the seventh, plus 2z cubed, all divided by the square root of 5z to the fifth plus 16z to the seventh. Okay, so for this one, let's recall, maybe you recall this from pre-calculus, that secant of theta is 1 over cosine theta. So the limit as z approaches infinity of 1, or will we rewrite this as 1 over cosine 4z to the 4 times the fraction e raised to the z to the seventh plus 2z cubed over square root of 5z to the fifth plus 16 z to the seventh. So to solve this one, we will just divide by the biggest power of z in all terms, which in this case, when you look at everything, it's going to be z to the seventh. So if we do that, that gives us the limit as z approaches infinity of 1 over cosine of 4 over z to the cubed, because when you divide by z to the seventh, the z to the 4 will cancel out and you're left with z cubed on the bottom. Then we will have e raised to the 1 plus 2 over z to the 4 all over the square root of 5 over z squared plus 16z, or 16 times 1, sorry. So that gives us 1 over cosine. Well, let me explain before I write this down, because I know you probably haven't worked these problems before. So the behavior of all of these as we go to infinity, well, e to the 1 is just going to stay e because it's a constant, and so is 16. Now the rest of them, they're all divided by a power of z. Well, as the z approaches infinity, as the denominator gets larger in the fractions, they're going to get infinitely smaller. So they're just going to approach 0. So we are going to have 1 over cosine of 0, and that's times e plus 0 over square root of 0 plus 16. And that gives us 1 over 1, because cosine of 0 is 1, times e over square root of 16, which gives us e over, well, technically plus or minus e over 4. And that is our limit for this. And that is it for problem 6. All right, problem 7. We are asked to find an interval of length 1/2 in the interval 0 to 5 containing roots of the equation x squared minus 3x equals 0. And then we are asked to graph the function and show why they exist using the intermediate value theorem. Okay, so let's start off by finding the roots of x squared minus 3x. Well, we can just factor out an x. We have x minus 3. So our roots are going to be x equals 0 and x equals 3. And both of these are in the interval 0 to 5. So we need intervals of length 1/2. So let's choose intervals 0, 1/2, and 5/2 to 3. So now let's make a graph of this. So let's make a table of values. We'll have our x and y values. So we have 0, and then when we plug it into the equation x squared minus 3x, that gives us 0. Then for 1, we have -2. And then for 2, we have -2. And then for 3, we have 0. For 4, we have 4. And then for 5, we have 10. So let's make a plot of this graph. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is in the y, this is the x, and then we have 1, 2, 3, 4, 5, and then we will have -1 and -2. So let's plot our points here. And then we have 4, 4, and 5, 10. So our graph is going to look something like this on the interval. We'll see if I can make it go across all the points. Yeah, it's going to look something like this. So, actually, that arrow does not need to be there because we're only focusing on the interval 0 to 5. Okay, so when we look at this graph by the intermediate value theorem, this graph contains 0, 1/2 and the interval 5/2 to 3. And we can see that by the points that we made and the line that we drew. And that is it for problem 7. Now for the last problem from the set, problem 8. We are asked to show that the limit as x approaches 121 of the square root of x equals 11, and then we need to show that if 0 is less than the absolute value of x minus 121 is less than 0.01, then the absolute value of the square root of x minus 11 is less than this number 0.000455. And then for part B, we are asked to find a value of delta such that if 0 is less than the absolute value of x minus 121 is less than 0.01, then the absolute value of square root of x minus 11 is less than 10 to the negative 4. So this is using the formal definition of a limit, the last thing that we talked about for this first part of Calculus 1. So let's work this one out. So let's start by relating to the gap x minus the absolute value of x minus c. So we write it as square root of x minus 11 equals, or the absolute value of the square root of x minus 11 equals the absolute value of x minus 121. So let's try to rationalize this. Do some algebra to rewrite this. So, or excuse me, this is technically pre-calculus. X minus 121, and then we'll divide that by it's not the absolute value, just the regular value, square root of x plus 11. So square root of x plus 11 is greater than 11 when x is greater than 0. So we can write this as the absolute value of x minus 121 over square root of x plus 11 is less than 11 epsilon. Hold on, sorry, getting a step ahead. As the absolute value of x minus 121 over 11. So now let's choose a delta, which is in terms of epsilon. So let's do absolute value of the square root of x minus 11, and then this fraction is less than 11 epsilon. So then we have absolute value of the square root of x minus 11. It's supposed to be 11 is less than 11 epsilon over 11, which is epsilon. So thus, delta equals 11 epsilon. So therefore, if 0 is less than the absolute value of x minus 121, which is less than delta, then absolute value of the square root of x minus 11 is less than epsilon, where delta is epsilon. And by making this statement, which is the formal definition of the limit, we have showed that the limit as x approaches 121 of square root of x equals 11. Now, let's look at the two parts that branch off of what we just showed, or that want us to solve from what we just showed. So for part A, we're going to let 0 be less than the absolute value of x minus 121, which is less than 0.01. So then we can subtract 121 from both sides, and we get 120.99 is less than x is less than 121.01. So square root of x is less than the square root of 120.99, which is less than 10.995, and the square root of x plus 11 is greater than 21.9995. I forgot a 9 over here. So therefore, the absolute value of square root of x plus 11 is less than 0.01 over 21.995, which equals 0.000455. And this was what we were given. So, yep. All right, for part B, let's let 0 be less than x, the absolute value of x minus 121, which is less than 0.01, and the absolute value of square root of x minus 11 less than 10 to the negative 4. So then we have the absolute value of x minus 121 over 11 is less than 10 to the negative 4. So thus, absolute value of x minus 121 is less than 11 times 10 to the negative 4, which is 0.0011. So therefore, we can let delta equal 0.0011. Yep. So by just going off of the formal definition of the limit and rearranging things, we were able to find these, well, show for part A, and then find the value that we needed for delta. Now, our next topic we're going to look at is differentiation. So, a big topic of differentiation is going to involve these things called derivatives. So, what is a derivative? Well, there are three ways it is defined. One definition is a rate of change. Another definition is the slope of the tangent line. And the third one is the limit of a difference quotient. And this one is the more formal definition of a derivative. So if you recall, when we were looking at limits, we had this equation delta f over delta x equals f of x minus f of a all over x minus a, and that was called the average rate of change. So let's suppose we introduce h, which is equal to x minus a. So then we have h equals x minus a, which implies that x equals a plus h when we rearrange things. So now we have delta f over delta x equals, excuse me, this is supposed to be delta h, f of a plus h minus f of a all over h. And if you remember, we kind of worked a problem that was sort of similar to this back when we were doing limits and rates of change in the problems that we just worked out not too long ago. So let's visualize this graphically. So let's plot this out. So y, then our x-axis, then let's just say we have this graph right, or this curve right here, and then we have a point P and a point Q. Then we have this line going through both points. And then let's say that P is at point A, and then Q is at point A plus H. So the distance from here is from A to A plus H is H. The distance from A plus H to Q is f of A plus H minus f of A. So this is just giving a graphical interpretation of this equation and how it works. Basically, the h is just an arbitrary distance between 2 points. And then, of course, our y, going up to point Q from A plus H, well, that's just plugging everything into the function. Because, the function f, it's like y equals mx plus b. Well, we get y by plugging in our values for x, or in this case, a, and then, of course, h for the change. So the derivative definition. So the derivative of f at a point is the limit of the difference quotient. That is, if it exists. So it's written as f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. And this is probably looking similar to one of the problems that we worked out previously. So, like I said before, this is called f prime of a. This notation means f prime of a, and the little apostrophe is called prime. So when the limit exists, we say f is differentiable at a. So again, we have f prime of a equals the limit Now we write as x approaches a of f of x minus f of a all over x minus a. Now let's look at the tangent line. So the definition of a tangent line is to assume that f is differentiable at a. So the tangent line to the graph y equals f of x at p equals the point a, f of a, is the line through p of slope f prime of a. So in equation form, we have y minus f of a equals f prime of a times x minus a. So the prime notation for a derivative such as y prime or f prime of a, etc., or f prime of x derivative, was introduced by French mathematician, and I believe, I'm not 100% sure this is the right way to pronounce this name, but Joseph Louis Lagrange, who lived from 1736 to 1813, but a more standard notation was developed by, and again, I'm not sure if this is the right way to pronounce his name or not, but Gottfried Wilhelm von Leibniz. And he lived from 1646 to 1716. And this notation that he came up with was dy over dx or df over dx. So basically, instead of writing y prime or f prime of x, we would write it as dy over dx or df over dx. So we now have several rules to look at for derivatives. below is a table summarizing them. And instead of writing out the table, because this is a very long table, I'm just going to copy and paste it from my previous notes. And then we will look at all these derivative rules and how they work. And we're just going to look at the rules generally right now. And then when we go to the examples after this section, you'll see a lot of them being applied. So here are the tables of all the rules and the formulas, or most of the rules and formulas we have for derivatives. So we have the constant rule. The derivative of a constant is equal to 0. For the x rule, when you take the derivative of x, it's equal to 1. For the power rule, when you take the derivative of x raised to the n, it's equal to x raised to the n minus 1 times n. For the sum and difference rules, when you have the sum of two functions and you're wanting to find the derivative of them, you can just find the derivative of each individual one and add them together, and similar for the difference between them. For the constant multiple rule, you can just multiply a constant times a derivative. For the number e for the exponential function, well, the derivative of e to the x is just e to the x. Now there is a further expansion on an exponential function, and we will talk about that later. It's actually not in this table, but because we will we'll kind of work it out in the notes that were for this section. So for the product rule, when you have f g prime to the x, well, that's equal to f prime of x times g of x plus f of x times g prime of x, where fg and fg is differentiable. Well, here's a fun way to memorize this rule. This is a fun way I learned to memorize it a while ago. So we have n out x, where n is f is g. Well, that's equal to dn out plus nd out. That's a kind of a fun way for me to remember the product rule and what stuck with me all these years. For the quotient rule, well, you can see the equation right here for the quotient rule. I'm not gonna tell you all those terms because you should know what they are by now. But fg and f over g are all differentiables in assumption, and g of x is not equal to 0. Well, here's another fun way to memorize this, because this can be a hard rule to memorize or a hard rule to memorize by itself, and this can be kind of a fun way to make it easier to remember. So say f is high and g is low, so you have high over low. Well, that's equal to low d high minus high d low all over low low. So low d high minus high d low all over low low. That's just a fun way to remember. Low low, low low, low low, low low. These are all the trigonometric functions, so you can just look at them right here and pause if you need to remember them or try to memorize them. But a fun way to remember for the trigonometric functions, notice how the derivative of cosine, cotangent, and cosecant, the sign changes, it's a negative. Well, this is a fun way for me to remember which ones change the sign and which ones don't. C means to change the sign, because cosine starts with a C, cotangent starts with a C, and cosecant starts with a C. And when you take the derivative of that, it means to change the sign. For the chain rule, when you have f of g of x, and you're wanting to find the derivative of that, and you're assuming f and g are differentiable, well, it's f prime g of x times g prime of x. And this kind of goes off into a composite function too. F of g, that's basically the same thing as saying f g of x. F of g of x equals f g of x is differentiable. That's an assumption for this chain rule. And you'll see the chain rule be used a lot with differentiation. These are the inverse trigonometric functions. Now, these don't yield a trigonometric function. They instead yield these fractions with, like the square root of 1 minus x squared. And I believe, if I remember correctly, I think these kind of stem off from like the Pythagorean theorem, and that's how these derivatives were proven. So you can look more into those, and you can just look at them here. I'm not going to explain all, or tell you what all of them are, because you can see them right here. For the logarithmic function, when you take the derivative of a logarithmic function, it's equal to 1 over the natural log of the b, where b represents the base of the log function of x. And of course, b is assumed to be greater than 0, and b cannot be equal to 1. For the natural logarithmic function, the derivative of that is equal to 1 over x. And if we have, now that's only if you have x. Now if you're taking the natural logarithm of a function, it's equal to f prime of x over f of x. And this is the general exponential function. So say this was like, b of x, it's like, 2 raised to the 4 or something like that. Well, that will be equal to ln of 2 times 2 raised to the 4. And then these are hyperbolic trigonometric functions. Again, not going to go through explaining all of them. You can just look at their formulas here. And then, of course, you also have inverse hyperbolic trigonometric functions and their derivatives. And also an important thing to note, the c, the little c means change the sign that I use for the trigonometric functions, that is not useful for hyperbolic trig functions. It does work for the trig functions and the inverse trig functions, because cosine, cotangent, and cosecant all change the sign for the trig and the inverse trig functions, but not for the hyperbolic functions. So do not use that rule for that. That only works for the trig functions. And that's just kind of a general looking at all of the derivatives. And there's, of course, a lot more. This isn't all of them, but these are kind of like some of the core ones that you'll probably will encounter. So let me change my pen size, make this a little thicker. We will work example problems where you can see some of these being used. And of course, I also have timestamps in this video too. So if you want to use a timestamp and skip to the examples, because it's going to be after we look at all these notes about differentiation that we'll work some examples with them. So you can just skip to that if you want to see some of these being used for the example problems and go through the ones that I have to see some of these being used. All right, let's change colors here because we're going to look at another topic, and that topic, let's go with pink. That topic is going to be higher derivatives. So when a function is differential or differentiated more than once, we say we have a higher derivative of the function. So if we have f prime prime of x, or f double prime of x is another way this is often described, was equal to d over dx of f prime of x. And this is also called the second derivative. And here's a more general way to write it. And you can write it as Fn of x equals d over dx of f of n minus 1 of x, where n is a natural number. And this fancy n that I did, that's a Blackboard font for natural numbers, which is a set. You can look at my mathematical proofs lectures or just Google that if you want to understand what that means and what a natural number is. So n, this can be a natural number or a number of apostrophes, but generally after f double prime or f prime prime prime, it is very common to see f of 4, f5, etc., meaning the fourth derivative and the fifth derivative and so on and so forth. So it's much more common to see that when the derivatives get higher than the second or third derivative. So an example of this find f prime prime x of x squared minus 5x times 4e to the 4x. So let's start by finding f prime of x. That's equal to 2x minus 5 e4x plus x squared minus 5x 4e to the 4x. So how do we determine this derivative? Well, first, notice that we have two functions being multiplied together, so we have to use the product rule. And we have to use the exponential rule. Now, this is different than the number e that we mentioned earlier, and the exponential rule is if you have d over dx of e raised to a function g of x, that's equal to g prime of x times e g of x. And this kind of stems off from the chain rule. The chain rule kind of helped develop this for the exponential function. So if we're looking at d over dx of e to the 4x, that's equal to 4 times x1 minus 1. So that's going to be x0, which is just 1. So that gives us 4e to the 4x when you take the derivative of it. And of course, technically we also have the constant rule being applied to here, but you'll kind of just know that when you do more of these, you'll just realize that, when you have 4 times e to the 4x, oh, well, let's find the derivative of e to the 4x and then just multiply that by 4. You don't even have to really think too much about that. So now let's find the second derivative. And I'm just going to give it to you, and you can try this on your own if you want to figure out using the product rule and exponential rule, because realize now we have two products and they're being added together, when you take the derivative of the first derivative, f prime of x. So you'll have to do the product rule and the exponential rule, and also you technically have the sum rule too, but you would do the product rule first for both of these and then do the sum rule and add them together. So that's going to give you 2e to the 4x plus 2x minus 5 times 4e to the 4x plus 2x minus 5 times e to the 4x, plus x squared minus 5x 4e to the 4x. And I think I may have made a mistake here. 4e to the 4x. Oh, I was jumping ahead in my notes. This is just supposed to be e to the 4x. Sorry, because I was thinking when we were doing the chain rule that we would have 4e to the 4x, but then you would have to multiply that by 4 if that was staying up there. So, yeah, we're good. We're good on this now. My apologies for that. All right, now let's change colors here. We will look at the next topic. Yeah, let's go with green. And that next topic is going to be rates of change. So recall that delta y over delta x equals f of x1. I guess we should technically write it as y of x1 minus y of x naught all over x1 minus x naught. So if you remember, we just needed to recall that formula. So a new and much easier way to find the instantaneous rate of change is to use the formula f prime of x naught equals the limit as delta x approaches 0 of delta y over delta x, which equals the limit as x1 approaches x naught of f of x1 minus f of x naught all over x1 minus x naught. So, in simpler terms, just plug the point into the derivative to get the instantaneous rate of change. So an application of this is physics. And one such topic that uses something like this is projectile motion So, what is projectile motion? Well, let's say that you are throwing something. Say that you throw a little ball in the air. This might be like some kind of little wiffle ball or pickleball. Well, when you throw such an object in the air, a general behavior that physicists have determined that describes something like this is basically a parabolic motion. So it moves in a parabola-like motion, and I'll try to make that a little bit more straight, not as loppy. It basically moves in a projectile motion as it goes from one point to another, and the y-axis is the distance it travels in meters, and the x-axis is time. That's how much the object moves as it travels, as time moves on. So, a general equation for something like this is S of t. That's a really, let me see if I can make that S a little clearer, equals S naught plus V naught t minus 1/2 gt squared. And this S naught, that's basically S of 0, and that's the position at time t equals 0 seconds. And then V naught, that's V of 0, that's the velocity or speed at time t equals 0 seconds. And then G is the gravity constant. And that is 9.8 meters per second squared, or 32.2 feet per second squared. So, velocity or how fast an object is traveling is the derivative of st. And of course this is called projectile motion, but sometimes it's called the position equation, because when you plug in your time t, you figure out the position of the ball or of the object that's moving. So S prime of t equals V of t. So, this is kind of a general projectile motion graph. So at this point, this instantaneous rate of change represents the velocity or speed that the object is moving. So let's look at an example. What is the velocity of a ball at 4 seconds if it starts at rest 5 meters from the ground. Okay, so we need to look at what the problem is asking. The ball starts from rest, so our initial velocity is 0 meters per second. And then we are told that our initial position, that it starts 5 meters from the ground, so it starts at 5 meters. So when we plug these values into our position equation, we get s of t equals 5 meters plus 1/2, 9.8 meters per second squared, t squared. And then we want to know the velocity of the equation, so we need to find s prime of t. That's going to be 0 because 5 meters is a constant. And then when you take the derivative of 1/2 times 9.8 t squared, you'll bring the 2 down and that cancels out the 1/2. So that leaves you with 9.8 meters per second squared times t. And then we wanted to know the time at 4 seconds, so we can plug that in. Equals 9.8 meters per second squared times 4 seconds gives you 39.2 meters per second. And that's the speed of the ball at 4 seconds, or if we were to use the more mathematical term, the instantaneous rate of change at 4 seconds. So, recall this equation, f prime of x naught is approximately equal to f x naught plus h minus f x naught all over h. So if we set h equal to 1, we can say that f prime of x naught is approximately equal to f of x naught plus 1 minus f x naught. And this is an important equation to remember. And this is more useful when x equals x naught. So an application would be marginal cost. And marginal cost has a formula that marginal cost equals c of x naught plus 1 minus c of x naught. All right, now let's change colors here and we'll look at a different topic. And that topic is going to be implicit differentiation. So let's suppose we have the equation, the fourth derivative of y plus cosine of y equals x negative 3 plus 2xy. or excuse me, that's actually y to the fourth, not the fourth derivative of y. And we wanted to find the derivative. So we want to find dy over dx. So we would have d over dx y to the fourth plus d over dx cosine y equals d over dx x to the negative third plus d over dx 2xy. So this is where implicit differentiation is used. So it has two key steps. And the first one is to take the derivative of both sides with respect to x, or whatever your differential is in the denominator. And what I mean by that is if you have d over dx, then the differential is x, because it's in the denominator. It's the one that you're differentiating with respect to. And then the second step is to solve for dy over dx, or whatever your rate is, by collecting terms on the other side and the remaining terms onto the other side. So let's look at how to differentiate. If we go back to this problem up here that we were looking at, because this is the one we're going to try to do implicit differentiation on to give an example of doing it. So how do we differentiate d over dx y to the fourth and d over dx of cosine of y? So we can use the chain rule. So d over dx of f of x to the fourth. Sorry, I should have defined, let's let f of x equal y. So d over dx of f of x to the fourth equals 4f of x to the third. with respect to df over dx. So if we just substitute y for f of x, we have 4y cubed dy over dx. And now let's let f of x equal cosine y. So we have d over dx of f of x, just plain f of x. That's equal to f prime of x with respect to df over dx. So if we plug in cosine of y, that's going to be sine y dy over dx, because the derivative of cosine y is negative sine y, if you remember that from the tables. So for d over dx of 2xy, let f of x equal y and use d over dx 2x f of x. Well, this is going to be the product rule, and we have dn out plus out, or in d out, f prime of x df over dx, which is going to give us, if we plug y back in, 2y plus 2x dy over dx. So we have 4y cubed dy over dx minus sine of y dy over dx equals negative 3x to the negative 4 plus 2y plus 2x dy over dx. And this is when we go back and plug in these terms that we found into our equation that we have up here. And now what we're going to do, we're going to move all the dy over dx terms to the same side. So we have 4y cubed dy over dx minus sine of y dy over dx minus 2x dy over dx equals negative 3x to the negative 4 plus 2y. That's supposed to be to the, that's supposed to be to the positive 4. I don't know where the negative 4 came from. Or wait, hold on. No, that's supposed to be to the negative 4. That's right. So we then factor out dy over dx, and that gives us 4y cubed minus sine of y minus 2x equals negative 3x negative 4 plus 2y. So then we get dy over dx equals negative 3x negative 4 plus 2y all over 4y cubed minus sine of y minus 2x. And this is our dy over dx that we found using implicit differentiation. And that's pretty much all there is to look at for implicit differentiation. So the last topic we'll be looking at for differentiation is, let's actually use, let's actually use the solid black. We are going to look at related rates. So, since derivatives describe rates of change, we can sometimes use rates when you sometimes use rates known, excuse me, wrong word, known to find other rates we do not know. So an example, let me try to make that more straight. Let's say we have water filling a tank. So let's draw a little cube here to represent the tank. And then we'll have a little spigot up here. Then let's change colors here to show the water filling it up. So we have the water coming in. Let me use a bigger pen color to get this filled up. And then we have it coming in. And then let's just say we've filled it up, filled the tank up with this much water. So we have water being filled up in a tank. And let me change my pen size. So let's suppose the tank has an area of 10 meters squared, and the tank is filling up at a rate of 0.6 meters cubed per minute. So we need to find the rate at which the is filling up. I wasn't sure if those words were going off the screen or not. At which the water level is rising. So we have the area, which we'll call A, is 10 meters squared. And then we know a formula for volume, or we know the rate at which the volume of the cube is filling up. It's filling up at 0.6 meters cubed per minute. So we need to find dH over dt. So we need an equation to relate the variables to differentiate them. So we will go back to geometry. So we have a rectangular tank. So we will use the equation the volume equals area times height. So we know the area, it's 10 meters squared, so we have V equals 10H. Then if we take the derivative of dV with respect to dt, that gives us 10 dH over dt if we take both variables with respect to time. And thus, we have dH over dt equals 1 over 10 dV over dt, because we just divide by t to solve for dH over dt. So, therefore, dH over dt equals 1/10 of 0.6. So that's 0.06 meters per minute. And that's our rate at which the tank is filling up. If we fill it up with a flow rate of 0.6 meters cubed per minute. And that's basically the whole idea of related rates. Basically what you're doing is you're given a rate and maybe another variable that you would know, like in this case the area of the tank, and then you just need to find an equation, and this often means you have to go back to some other math and figure out what equation you need to use. In this case, we used the volume formula from geometry. Then you differentiate them, solve for your rate, and then you can plug and chug, so to speak, to get your rate that you need. Now we will work some example problems for differentiation. So for the first problem, we are asked to find the derivative of kt equals 4t plus 1 using the limit definition. All right, this one is going to be pretty straightforward. So for this one, we will just use the limit definition. We have k prime of a equals the limit as h approaches 0 of k a plus h minus k of a all over h. Then we have, when we plug everything into the equation, we have 4 of a plus h plus 1 minus 4 of a minus 1 all over h. And as you can see here, we have a 4a, and that's going to cancel with this 4a right here. The ones will cancel too. And then that gives us the limit as h approaches 0 of 4h over h. And the h's cancel, and that gives us 4. So that's our derivative of this equation using the limit definition. For our second problem, we are given a tangent line y equals 7x plus 11 to y equals f of x at a equals 5, and we are asked to find f5 and f prime of 5. Okay, for this one, we pass through the point 5 and f of 5. So plug in 5 to the equation, and that gives us f of 5 equals, well, y of 5, because our equation is defined by y. That gives us 7, 5 plus 11. That gives us 46. So there's our f of 5, and now let's find f prime of 5. So recall a derivative is a rate of change or slope. So we have y equals 7x plus 11. Well, this is a standard linear equation, so 7 is the slope. So f prime of 5 equals 7. So we have f of 5 equals 46, and f prime of 5 equals 7. And that's our solution to the second problem. For our third problem, we are asked to estimate the derivative of fx equals tangent x at x equals pi thirds. So this one is a pretty involved problem, so I thought I just kind of wrote it out already, and we'll just kind of look at what's involved with doing this. So to find this one, we need to use the formula that was not mentioned earlier in the notes, and that is that f prime of a is approximately equal to f of a plus h minus f of a over h if h is small. So what we need to do for a problem like this, we need to make a table of values, and we need to approach both sides of the equation like you would for some limits, because if you remember, we did something like this for evaluating a limit, especially for evaluating the instantaneous rate of change at a point. So we will plug in some values for h. We'll do some really small values of h because that's an important key to this equation, to this formula. And we have a table of values here, and we plug it into our equation, f of a plus h minus f of a over h, which is tangent in this case, and we're evaluating it at pi thirds. So when we plug in these values of h, and we go from both sides from small positive values of h to small negative values of h, we can see that we approach a limit on, or that we approach a value for the derivative on both sides, and that is approximately, it comes out to be exactly 4. And of course, my accuracy on this is to 4 decimal places. The accuracy you use for different problems, it varies a lot. So that was just what I decided to use based off of the answers that I got for this. So that's what you need to do for the third problem. For the fourth problem, we are asked to find the derivative of f of x equals log base 10 of x over hyperbolic cotangent of x. Okay, for this one, we need to use the quotient rule. The logarithmic rule and hyperbolic trig rule. So for the quotient rule, if you remember the quotient rule, there's that fun little saying, low d high minus high d low all over low low. And that's what we're going to do. That's what we're going to do first. We're going to write out this derivative. So we have low, which is hyperbolic cotangent of x, and then d high, well, that's going to be the derivative of log base 10 of x. And if you remember, the formula for that was 1 over ln the base times x. And then we have high, which is our log base 10 of x, d low. So the derivative of hyperbolic cotangent, if you remember from the hyperbolic derivative rules equations, it was negative hyperbolic cosecant squared of x all over low. So we just have hyperbolic cotangent squared of x. So let's take a look at this further. So we can just simplify this a little further. Hyperbolic cotangent of x times 1 over ln 10x plus log base 10 of x hyperbolic cosecant squared x, and then all of this is going to be multiplied by 1 over hyperbolic cotangent squared of x. So basically what we're doing, we're just rewriting this fraction, and what's going to happen is we're going to cancel a hyperbolic cotangent here, and then that leaves us with 1 over ln 10 of x times hyperbolic cotangent of x plus log base 10 of x hyperbolic cosecant squared of x all over hyperbolic cotangent squared of x. So now let's try to put this in terms of sine, cosine, and tangent, just because that's generally a preferred way for these trig functions. So we will write this as 1 over ln 10 of x. Then we have 1 over tangent of x plus log base 10 of x times 1 over sine, or hyperbolic sine squared of x, all over hyperbolic cosine squared of x, all over hyperbolic sine squared of x. So these will cancel, and a simplified version of this in terms of tangent, sine, and cosine is hyperbolic tangent of x all over ln 10 of x plus log base 10 of x all over hyperbolic cosine squared of x. So, I mean, maybe it wasn't necessary to take these extra steps to simplify, because the first derivative we took right here using the quotient would have been fine, but just thought it would have been great to go over some trig rules and so some ways you can simplify this and try to write it in a way that may be easier or preferred by some people. Now on to problem 5. It states that suppose a doctor is looking at a plot of blood glucose of a patient after eating dinner. The plot consists of the blood glucose in milligrams per dl versus time in minutes, and has the equation b of t equals 80 plus 73 e raised to the negative 0.0019 times t minus 30 squared. So what is the rate of blood glucose after 12 minutes? And about how long does it take for the blood glucose to stop rising? And we are asked to look at the figure below for a general sketch to see the plot behavior. So this is kind of a plot of this equation b of t, just a general plot of it, so we can kind of see the behavior of it. So, and this may be useful in helping us figuring out how long does it take for it to stop rising, but let's take a look at the rate of blood glucose after 12 minutes first. So to figure out the rate of the blood glucose, we need to find the derivative of this equation. So we need to start off by finding b prime of t. So b prime of t is going to be equal to 0 plus 73 times negative 0.0019 times d over dt t minus 30 squared and then e negative 0.0019 t minus 30 squared. So let's take a look at what exactly is going on here so you can understand what the derivatives we are doing here. So we have the exponential rule, and we also have the constant rule too. So if you recall the exponential rule, we have d over dx, e of gx. That gives us g prime of x, e to the gx. And then we have our term d over dt, t minus 30 squared. Well, this is going to involve the chain rule. So that's going to give us 2 times t minus 30 times d over dt, t minus 30. And that's going to give us 2 times t minus 30 times 1. And that's 2 times t minus 30. So we have our equation b prime of t equals negative 0.266 t minus 30 times e to the negative 0.0019 t minus 30 squared. So this is the derivative of this equation up here. When you take the derivative of that 80, that constant value is 0, and then you do an exponential rule, a constant rule, and then a chain rule on top of that, because you have t minus 30 squared here in the exponential equation. And then when you plug all that back in, this is what you get for the derivative. So now we know the derivative, so let's plug in 12. So b prime 12, that equals negative 0.266. 12 minus 30 e to the negative 0.0019. 12 minus 30 squared. And that gives us 2.587 mg over dl over minutes. So that's the rate that the glucose increases at 12 minutes. So for the second part, notice that the blood glucose stops rising when we reach our maximum glucose level, or when our change is 0. Because if you recall from the shape of our graph, well, I'll just go up here to the graph actually. Right here at our maximum value, if we were to take a slope here, it would just be a constant line. So slope would be equal to 0. And that would be at our maximum blood glucose value. So, or blood glucose level. So we need to set b prime of t equal to 0. So we go back to b prime of t, we'll just have 0 equals negative 0.266 t minus 30 e to the negative 0.0019 t minus 30 squared. So this equation, it's going to be kind of tricky to isolate t by itself to figure out what the time will be. So we instead just have to look at what we have in the equation and see if we can find another way to figure out what the time t is going to be to get us to when our change in glucose is going to be 0. And then from there, the blood glucose just keeps decreasing and eventually stabilizes. So we only get 0 when t minus 30 equals 0, since 0.266 and e to the negative 0.0019 t minus 30 squared can never be 0, because the it's an exponential function, and that function just keeps constantly increasing. So we have t minus 30 equals 0. So we can just rearrange and we get t equals 30 minutes. And that's when the blood glucose stops rising after eating a meal. And that's pretty much it for problem 5. Now let's take a look at problem 6. So for problem 6, we are asked to find the derivative at the point 1, 1 of the heart, which is given by the equation x squared plus y squared minus 1 all cubed equals x squared y cubed. And this is kind of a little graph of the equation that was made using a Desmos online graphing calculator. And this is just I just love this graph. This is such a really sweet graph, and it's always nice to just see a heart being made using math, which I think is really sweet and really adorable. So now let's see if we can figure out what the derivative of this graph is going to be. So this is going to be an equation where we're going to have to use implicit differentiation. So we have d over dx of x squared plus y squared minus 1 cubed equals d over dx of x squared y cubed. So for this, we will have to use the chain rule. And then for this term, we will have to use the product rule. So we have d over dx, x squared plus y squared minus 1 times 3 x squared plus y squared minus 1 squared, and that equals 2xy cubed. Because the product rule, if you remember, it was out dn minus nd out. So out is our y cubed, and then dn is going to be 2x. And then we have nd out, so n is x squared, and then d over dx y cubed. So what we are going to do for this term, we are going to let y equal f of x, and we have now we have d over dx of x cubed. Well, that's going to give us 3 f of x squared df over dx. And for this y term right here, it's basically the same thing. So I'm not going to go through all of that and just go on and give you that derivative using that substitution. So we have, when we do d over dx of everything in here, we, on this term on the left side, we have 2x plus 2y dy over dx times 3 of x squared plus y squared minus 1 squared equals 2xy cubed plus 3x squared y squared dy over dx. So now let's rearrange and put all the dy over dx terms on the same side. So we have 2y dy over dx, and that's all times 3x squared plus y squared minus 1 squared. And we have minus 3x squared y squared dy over dx equals 2xy cubed minus 2x times 3x squared plus y squared minus 1 squared. Okay, so now we can factor out dy over dx. So that's going to give us dy over dx 2y. Let's just go on and multiply them. 6y x squared plus y squared minus 1 squared minus 3x squared y squared equals 2xy cubed minus 6x x squared plus y squared minus 1 squared. Then we divide by dy over dx, and that gives us our equation 2xy cubed minus 6x x squared plus y squared minus 1 squared all over 6y x squared plus y squared minus 1 minus 3 x squared y squared. Yeah. Okay, so now we need to plug in our point 1, 1 to figure out the derivative at that point. So dy over dx at 1, 1, we just plug in 1 for x and 1 for y, so we have 2, 1, 1 cubed minus 6, 1 squared plus 1 squared minus 1 squared all over 6, 1 squared plus 1 squared minus 1 minus 3, 1 squared, 1 squared. So that gives us 2 minus 6 times 1 all over 6 times 1 minus 3. So that gives us negative, let me write it down here, oops. So that gives us negative 4/3, and that is our derivative at that point. The derivative at our sweet little heart here of 1, 1. Or at the point 1, 1, at 1, 1, at the point 1, 1. All right, on to the last problem for differentiation. So the last problem, we have a refrigerator is being lifted up into a room, and a pulley system is installed as shown below. The towing machine pulls the rope at 5 meters per second. How fast is the fridge traveling? Okay, so for this one, we need to use the Pythagorean theorem to determine an equation relating them. because if you look at our diagram up here, we have our little towing machine that is in the room and it's connected to a pulley which is on the roof, and that towing machine is about 7 meters away, or is 7 meters away from the pulley, and the fridge is 24 meters from the ground. And then of course we can make a, uh, a hypotenuse to connect them, and we'll just call that L, and we'll figure out the length of that because that's going to be key to figuring this out. But our 5 meters per second is going to represent not our change in x, which would be 7 meters, because that's going to remain constant. That distance is not going to change. That's going to be our dl over dt. That's going to be our change in our length and our hypotenuse of this triangle. So our Pythagorean theorem, we have L squared equals x squared plus y squared. So when y equals, we're going to call it negative 24 meters because the fridge is 24 meters from the ground, we have L equals the square root of 7 squared plus negative 24 squared equals the square root of 625 is 25 meters. So now let's differentiate. So we have d over dt of L squared equals d over dt. This is going to be 7 squared because this is going to be a constant length that isn't going to change, d over dt of y squared. So this is just going to cancel out because that's going to be equal to 0. So we have 2L dl over dt equals 2y dy over dt. So we have dl over dt, and we already said that's going to be negative 2 meters per second because the length is going to decrease. We're going to solve for dy over dt, or excuse me, this is supposed to be 5 meters per second. So we have dy over dt equals, when we divide by 2y to isolate dy over dt, that gives us L over y dl over dt. So let's plug in L equals 25 meters, y equals negative 24 meters, and dl over dt is negative 5 meters per second. So we have dy over dt is negative 25 meters over 24 meters times negative 5 meters per second, and that gives us approximately 5.208 meters per second. And that is how much the fridge is rising if the towing machine pulls the rope at the speed that it is. And that is it for the problems for differentiation. Now we will look at applications of the derivative. So basically what we are going to look at in this section is we will look at some uses of derivatives. So, one topic we are going to look at is linear approximation. So, linear approximation focuses on small changes and its effects. So, the definition of it is if f is differentiable at x equals a and delta x is small, then delta f is approximately equal to f prime of a delta x, where delta f equals f of a plus delta x minus f of a. So therefore, f of a plus delta x is approximately equal to f of a plus f prime of a delta x. And this is an important equation to remember, so we'll put a box around that. So let's take a look at this graphically. So let's make a line here. We have our y-axis and our x-axis. We'll have a point A, then another one, a plus delta x. Then we'll have f of a, and then f of a plus delta x. Then let's make our line going here. This is our line y equals f of x. Then we'll make our points. Then we will try to draw out a tangent line as best that I can. I'm not the best at doing these. But let's just say that it is a tangent line. At the point a, f of a, and then we will make this point right here, then we will draw this out right here, and this line right here is going to be known as delta x, and then this area right here, I'm trying to get it to erase. There we go. The distance from this point to this point is f prime of a delta x. And then what we have here, we will call this delta f, and that's going to be the actual change. So it's basically just showing for our tangent line what is the difference between it and our real line. So often linear approximation is accurate enough to the actual change. So this lets us use a new definition for differentials. So if we have dy equals f prime of a dx, where delta y equals f of a plus delta x minus f of a, well then delta y is approximately equal to dy. Or if we were to put this in f terms, we would say that delta f is approximately equal to f prime of a delta x. So we can linearize a graph by introducing Lx, and we will say that it is centered at x equals a. So we then have f of x is approximately equal to Lx, which is equal to f of a plus f prime of a x minus a. This is another important equation to remember, where x is close to a. So when determining the percent error of a linearly approximated value, to its true or more accurate value, we can use the formula percentage error equals the absolute value of error over actual value times 100%. This is again another important formula to remember. And we can also look further into the size of the error by using this formula, or this value e, which is equal to the error, which is equal to the absolute value of delta f minus f prime of a delta x. with an error bound, which is defined by e is less than or equal to 1/2 k delta x squared. This is another important formula to remember, where k is the maximum value of the absolute value of f double prime of x on the interval a plus delta x. So I'm going to copy and paste the graph down here again to kind of give you a representation of what the error is graphically. So graphically, if we were to understand what the error is, if you look at this point on the tangent line right here, if we look at the distance to it from our actual line, that describes the error. And that's just plain and simple, because this is the same graph that we had earlier, what the error represents graphically. Okay, let's change colors here, and we will look at the next topic in this section, and that topic is going to be extreme values. So, derivatives help us find minimum and maximum values of functions. And this is very useful in many applications, such as finding the max temperature across a surface, or the maximum concentration of medicine in a patient's blood, or whatever other such applications could be used to describe something like this. So let's look at a definition here. So we are going to let f be a continuous function on an interval I, and let a be an element of I. So then fa is the absolute minimum of f on I if f of a is less than or equal to fx for all x that is in I, or it is the absolute maximum of f on I if, it's supposed to be if up here, f of a is less than or equal to f of x, or sorry, excuse me, greater than or equal to f of x for all x and I. So let's say we have this graph here. Say it represents a concentration in a patient's blood, CT, across or versus time, hours, and this is our graph right here. Well, we would say that this value right here is the maximum. Or if we have this plot right here, we have our y-axis and our x-axis. If we have a graph such as this, then this value right here would be the minimum. So this kind of leads to a theorem that says if a continuous function f is bounded by an interval I, which is equal to the interval of a to b, then it has both a minimum and a maximum value. So if we have a plot like this, on the interval a to b, and the graph behaves something like this, then this value would be the max, and this one would be the min. So these points on an interval are referred to as a local minimum and a local maximum. So if there is more than one min or max, then the lowest or highest is called the absolute maximum or minimum. So basically, if we have a point and we're just looking at it on this interval, and like above, if we can't show that it is the lowest or the highest value on the entire function f, then it is just a local minimum or a local maximum. But if it is the lowest or the highest value on both this interval and the entire function, then it is the absolute maximum or minimum. That's essentially what this is saying. So here's kind of a graph that expands on this a little further. We have the y-axis and the x-axis. Then our graph sort of goes like this. This is on the interval a to b. Well, at this point, it is a local min. Then this point will be a local max. And then this point will be the absolute min. So minimums and maximums are called critical points of a function. And we can find these points by using derivatives. So, say we have a graph here. We have the y-axis, then we have the x-axis. Then the graph is something like this. So notice that all of our mins and maxes, that the tangent line is constant, or the slope is 0. And this is how we can determine these critical points. So, critical points are where f prime of c equals 0, or f prime of c does not exist. And an example of one where it does not exist, if you have this graph y and x, and then the graph does something like this, then it does not exist here. And this specific behavior is called a cusp. So now let's take a look at Fermat's theorem on local extrema. So this theorem states if f of c is a local min or max, then c is a critical point. And here's another expansion on the theorem. If f is continuous on the interval a to b, and f of c is a min or max value on the interval a to b, then c is a critical point or an endpoint on the interval a to b. Now, the last theorem that we're going to look at for this particular part of extreme values is Rolle's theorem. What this theorem states is that if f is continuous on the interval AB and differentiable at the point AB, then there exists a number c between a and b such that f prime of c equals 0 if f of a equals f of b. And that's all we're looking at for extreme values, so we will change colors now. And we will start talking about the mean value theorem. So, the mean value theorem states that a secant line on a graph is parallel to a tangent line on the same interval. So here's a little graphical representation of what something like this means. So we have our x and our y axis. And then let's say we have the graph is going something like this. And then let's say that this point we call it A, and then this point we call it B, and then we have our point C. So if we have this secant line going through A and B, then f of B minus f of a over b minus a represents the slope of that. And then at point C, we'll just have the tangent line going through. And this is the slope f prime of C. And that's basically the mean value theorem in simple terms, what it means. So f is continuous on the interval a to b and differentiable at the point or on AB. So understanding this, we can look at function behaviors further. So let's take a look at monotonicity. So what is monotonicity? Well, monotonicity essentially means the behavior of something and for this case it's going to be, is it increasing or decreasing? So let's take a look at a theorem that relates to this. And that theorem is going to be, let f be differentiable on a b. So if f prime of x is greater than 0 for an x that is in AB, then f is increasing on the interval AB. And then if f prime of x is less than 0 for an x that is in the interval AB, then f is decreasing on the interval AB. Now let's look at another theorem, and this one states that let C be a critical point of f then f prime of x changes from plus to minus at C. So this implies that f of C is a local maximum. And then if f prime of x changes from negative to positive at C, then this implies that f of C is a local minimum. So let's look at an example relating to this. So let's analyze the critical points and monotonicity of the function f of x equals x to the 4 minus 2x squared plus 8. Okay, so let's find the derivative. So f prime of x equals 4x cubed minus 4x. And we can factor this out. Factor out of 4x, and that leaves us with x squared minus 1. And then we can also factor that out because that is a perfect square. So we have x minus 1 and x plus 1. So our critical points are going to be where x equals 0, x equals negative 1, and x equals 1. And I would assume you know how we get to this point, because basically what you're doing is you're setting f prime of x equal to 0, and you're just figuring out what all of those conditions need to be to make it 0. You're solving for all the x's. I know I didn't write that down, but I just wanted to clarify how we got to that point. Or let's plug these points back in to figure out the y-coordinate that matches with them. So we'll start with negative 1. That gives us 7. And then f of 0 equals 8. And then f of 1 equals 1 to 4 minus 2, 1 squared plus 8. That equals 7. So the critical points are negative 1, 7, 0, 8, and 1, 7. So now let's pick points to determine the graph behavior. So let's use negative 2, negative 1/2, 1/2, and 2. So f prime of negative 2 equals 4 times negative 2 cubed minus 4 negative 2. That gives us 4 times negative 8 plus 8, and that's negative 24. Now let's do f prime negative 1/2. That's 4 negative 1/2 cubed negative 1/2 equals 4 negative 1 8 plus 2, which gives us negative 1 plus 2 equals 3/2. And then so on and so forth for the next points. Just go on and give what those are. We have negative 3/2, and then f prime of 2 equals 24. So let's make a table and look at what we have. So let's take a table. Let's draw one out here. So we have 4 intervals that we're going to look at. We're looking from negative infinity to -1. And then we have from -1 to 0. Then we have 0 to 1. And then we have 1 to infinity. So if we take a look at what we have here, from -1 to negative infinity, when we plug in a point that's on that interval, like -2, we get a negative number, which was -24. So on this interval, we are decreasing. And then likewise, for the next interval, we have a positive value for a point that we plug in, so we are increasing. And then likewise, when we look at everything else, we'll see that we are decreasing. And then here we are increasing. So what we can conclude from this is our monotonicity. Now let's analyze our critical points. So our first point, -1, 7, since we're going from negative to positive, it is a local minimum. And then 0, 8, we go from positive to negative. So this is a local maximum. And then our next point, 1, 7, is negative to positive. So it is a local minimum. And that's pretty much all there is to understand about monotonicity and how we can determine graph behavior and some critical points using derivatives. So now we will change colors here and look at our next topic. And that topic is going to be graph shapes. So, derivatives can help us figure out the shape of a graph. So a very important shape of a graph is concavity, which concavity basically describes the way a graph bends. So there are 2 concavity shapes, and they are either concave up, and concave up looks like this, or concave down. And this is the shape you would see for something like this. So both behaviors are observed based on the slope of the derivative or the second derivative. So let's take a look at this graph. We have our x and our y-axis, and this is our point. Well, here at this minimum value, we're going to have f prime equal to 0. Now here, you're going to have f prime equals positive. And then here, you're going to have f prime is negative, because on the right side you have a concave up shape, and then on the left side you have a concave down shape, just like what you have a concave up and you have a concave up shape on both sides, but on both of these you are indicating the slope of the graph, and by looking at the slope of the slope, we can use second derivatives to determine concavity. So here is a theorem relating to this. It is a concavity test. Concavity test. So if f double prime of x is less than 0 for all x that is in A to B, then f is concave up on the interval A to B. And if f double prime of x is less than 0 for all x that is in the interval A to B, then f is concave down on the interval A to B. And we also want to know the point of inflection on a graph. And the point of inflection is essentially the point where concavity changes. So here's if you were to look at this graph right here, then if you notice at this point right here, this is concave down, and then this is concave up. Well, this P, this is the point of inflection, because we go from concave up to concave down on this graph. So here's a theorem about an inflection point test. So if f double prime of c equals 0, or f double prime of c does not exist, and f double prime of x changes signs at x equals c, then f has a point of inflection at x equals c. And we can also test critical points using the second derivative. So here's a theorem relating to this, and that is the second derivative test. So if f double prime of c is greater than 0, then f of c is a local minimum. And then if f double prime c is less than 0, then f of c is a local maximum. And then if f double prime c equals 0, it is inconclusive. So here is a fun mnemonic device that can help remember this test. So this guy, he has starry eyes and a smiley face. So this means that f prime of c is greater than 0, and he's a local min. And this guy, who has sad eyes and a little frowny face, well, this guy is a concave down dude, and he is Mr. Local Max. This is just a fun graph to remember. The graph behavior, but I'm going to try to make this guy a little bigger to kind of be as big as the one above him. There we go. Yep, this is just a little fun mnemonic device, a little sketch that can help you remember the second derivative test. So now with what we've gone over with extreme values, monotonicity, and the shape of a graph, we can go over graph sketching. So using what we just covered, we can now sketch graphs. So there are 4 steps for simple, or simple by definition steps we can use to sketch them. So for the first one, you need to find critical points of f prime of x and f double prime of x. And then for the second part, you determine their signs. And then for the third step, you identify maxes, mins, monotonicity, which, if you remember, that means whether it is increasing or decreasing. Concavity, and points of inflection. So some points may be asymptotes or cusp. In other words, they do not exist. And you can determine that by using or by looking at, your concavity and your behavior of the graph and everything like that. And then the fourth and final step, sketch everything. Because once you've done steps 1 through 3, you're pretty much ready to make your graph. So we will work an example problem where we do this, and you will see that when we get to the example problems, or if you want to skip ahead, because I should have a timestamp in the video where you can see this. Okay, that is pretty much it for the shape of a graph and graph sketching. So now let's change colors here. We will look at our next topic. Which one are we going to go with? Let's just go with solid black. We will talk about L'Hopital's rule. So L'Hopital's rule is a valuable tool for computing limits that are difficult to evaluate. So such limits are ones with asymptotic behavior, such as quotients. So here is the theorem. So assume that f and g are differentiable on an open interval containing a, and that f of a equals g of a, which equals 0. So then we can find limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x divided by g prime of x. And this is important to remember for evaluating these limits, where g prime of x is not equal to 0. So if the limit on the right exists or is infinite, this conclusion also holds if f and g are differentiable. For x near but not equal to a, and the limit as x approaches a of f of x equals plus or minus infinity. And the limit as x approaches a of g of x equals plus or minus infinity. And this also holds for one-sided limits. So there is also another rule for limits at infinity. So the theorem is that assume f and g are differentiable in an interval b to infinity, and that g prime of x is not equal to 0 for an x strictly greater than b. So if the limit as x approaches infinity of f of x and the limit as x approaches infinity of g of x exist, and either both are 0 or infinite, then the limit as x approaches infinity of f of x over g of x equals the limit as x approaches infinity of f prime of x over g prime of x. And this is provided the limit on the right exists. And a similar result holds for limits as x approaches negative infinity. Okay, so let's change colors and we will look at the next topic for this, and that topic is going to be applied optimization. So optimization involves looking at something and determining the best or the optimal value, design, condition, design, condition, etc. for it. So, applied optimization involves looking at an objective function that's important to remember, and using differentiation to optimize it. So there are 3 steps. Involved with applied optimization. And those steps are: 1, choose variables. 2, find the objective function and the interval. And then 3, optimize. So let's look at an example where we can do something like this. So let's say a chain of grocery stores sells approximately 12,000 grapefruits a month. So for every increase in price, the store loses approximately 4,000 sales of grapefruit per dollar. So what price should the grapefruit be to maximize profits if they buy them for 80 cents per grapefruit? Okay, well, let's take a look at this. We will start with the first step. We're going to let G represent the profits, P represent the price of the grapefruit, and then S of P is the profits of the grapefruit from the supplier, and N of P is the number of grapefruits sold. Okay, so let's take a look here. We are going on to the second step. So we are going to define G of P to be equal to S of P times N of P. Well, S of P, the profits of the grapefruit, is going to be P minus 0.8, because that's how much the grapefruits were bought for, 80 cents a grapefruit. And then N of P is going to be equal to 12,000 minus 4,000 P, because the store sells about 12,000 grapefruits a month, but each time the sale goes up, they lose approximately 4,000 grapefruits for each dollar. So if we just subtract 4,000 times whatever the price is, P, by 12,000, this should give us the number of grapefruits that we sell each month. Okay, so our price interval should be where the number of grapefruits equals 0. So we have 12,000 minus 4,000 P equals 0. Then we rearrange and solve for P, and that gives us 3. So our interval is going to be from 0 to 3. However, you do have to think logically here, and we will actually omit the point 3 for this particular problem, but in another problem you would put both of the bounds in, because you're not going to sell a grapefruit for 0 cents, because that's going to give you negative profits, and that would just make sense. So instead, we will just find the derivative of G of P, find a critical point there, test that one, and then compare it to $3 per grapefruit, and then see how that does, and see which one gives us the most profits. So we have, let's form our equation G of P. That's going to give us P minus 0.8 times 12,000 minus 4,000 P. Then when you FOIL everything together, you get 9,600 plus 8,800 P minus 4,000 P squared. So now we move on to step 3. Now let's find G prime of P. That's going to give us 8,800 plus, or minus, excuse me, minus 8,000 P. So now let's set G prime of P equal to 0. So 0 equals 8 minus 8,000 P. Then we rearrange. So we have P equals 1.1. So we need to evaluate GP at P equals 1.1 and P equals 3. So when we plug in G of 1.1, when you plug everything in, that will give you $14,400. Then when you plug in G of 3, that gives you $0. So profits are maximized when the grapefruits have a price P equals $1.10. And that's pretty much all there is to applied optimization to understand about it. You basically just have to figure out your variables, make an equation, determine your interval, and then your critical point, plug them all in, and see which one gives you the optimal value that you're looking for whatever your application is. Now we will move on to the last topic for this section. We'll change colors here. And that topic is going to be Newton's method. So, Newton's method helps us find a numerical approximation of zeros because most of the time finding the exact zero is difficult or impossible. So here is the theorem. And the theorem is to approximate a root of f of x equal to 0, you have to, 1, choose an initial guess x of 0, and this is close to the desired root. And then the second step you have to do, you have to generate successive approximations x1, x2, so on and so forth, where x of n plus 1 equals x of n minus f of x of n over f prime x of n. This is the key formula for Newton's method. So here's a graph to visualize what this is doing. So in this first graph, that we are drawing out. We have a graph that behaves like this. And we're trying to determine this point right here. So we start here. This is our initial guess, x naught. Then we'll plug it into the formula and we'll determine that it's that point. So then we plug that point in. And then it gets us to x of 1. And this is our first iteration. And then we do it again. Move this up a little more. So let's see if I can try to resketch this again. Oops. So we're still trying to guess our 0. So we do our initial guess, x of naught, and then it gives us this point, which then leads us to x of 1, which then, let's say it gives us this point, which then leads us to x of 2, and then so on and so forth. You would keep plugging it in, and eventually you would get really close to the actual 0. And this is our second iteration. And that's the difference between the first and the second iteration, is that we get closer to the actual 0. That's essentially what Newton's method does. Now we will work some example problems for applications of the derivative. So the first problem we are looking at is we are going to estimate the following using linear approximation. So we have e raised to the 0.4 power and inverse cosecant of 2.7 minus ln of pi. Okay, so let's see if we can estimate these using linear approximation. So we have the linear approximation formula, Lx equals f of a plus f prime of a times x minus a. Okay, so for a, our function is e of x, and we know that e of 0 equals 1. So let's let a be equal to 0. So then we have f prime of x, which equals e of x times the derivative of x, which is 1, which is e of x. So when we plug in 0.4, L of 0.4 equals e of 0 plus our derivative e of 0 times 0.4 minus 0, and that's going to give us 1 plus 0.4, which is 1.4. Now for the second one, our function is cosecant negative 1 of x minus ln of x. So f prime of x equals the derivative, this is the derivative of the inverse cosecant with the absolute value of x times the square root of x squared minus 1. And then the derivative of ln of x is 1 over x. So we will need to do two linear approximations since the inverse cosecant of x and ln of x will have different known values we want to use for A. So for inverse cosecant of x, recall that cosecant of x equals 1 over sine of x. So if you remember from learning some simple trig identities, if you remember that sine pi of 6 is equal to 1/2, well then cosecant of pi over 6 is equal to 1 over 1 over 2, which is equal to 2. So the inverse cosecant of 2 is equal to pi over 6. Because cosecant pi over 6 gives us 2, so if we do the inverse and plug in 2 into inverse cosecant, it will give us pi over 6. So let's choose a equal 2 as our point. So we have L of 2 is equal to inverse cosecant of 2, which is minus 1 over 2 square root of 2 squared minus 1 times 2.7 minus 2, and that gives us pi over 6 minus 0.7 over 2 square root of 5. And that is what we'll do for the inverse cosecant function. So now let's look at the ln x function. So for ln of x, remember that the natural log ln cancels out e, the exponential function. So we have, if we have ln of e of x, that will just give us x because those will cancel. So let's choose a to be equal to e raised to the 1, or just e. So we have L of 1 equals ln of e minus 1 over e times pi minus e. Well, that's going to give us 1 minus pi over e plus 1, and that comes out to 2 plus pi over e. So now let's add them together. And we have pi over 6 minus 0.7 over 2 square root of 5 minus 2 minus pi over e. And that is approximately the value of inverse cosecant of 2.7 minus ln of pi using linear approximation. Now on to problem 2. For problem 2, we have a copper wire of length 25 centimeters, and it is sitting at room temperature, which is 20 degrees Celsius. So we are asked to estimate its new length when it is heated to 44 degrees Celsius if the change in the length is defined by dl over dt equals kl, where k, the coefficient of thermal expansion, is 1.6 times 10 to the negative fifth degrees Celsius to the negative 1, or 1 over degrees Celsius. So let's figure out how to solve this, or let's go on and solve this problem. So to start, we need to find a value for dl over dt. So we have dl over dt, which equals kl. Well, we know k, and then we have our length. So dl over dt is going to be 4 times 10 to the negative 4 centimeters over degrees Celsius. Okay, so now we can find delta L, or the change in length, by multiplying by our temperature change. So we have dl over dt, and if we multiply that by dt, then that will give us dl, or delta L. So dt, we are told it's being heated to 44 degrees, so that's going to be equal to 44 minus 20 degrees Celsius. That's going to be 24 degrees Celsius. So delta L is going to be our dl over dt times 10 to the negative 4 centimeters over degrees Celsius times 24 degrees Celsius. And that gives us 0.0096 centimeters. So the new wire length is 25 plus 0.0096, and that's going to be 25.0096 centimeters. And that's the new length of the wire when you heat it up to this temperature, or at least a real close estimation of it. And this is again using linear approximation. Now for the third problem, we are going to look at a rainbow. And a rainbow, it is made by light reflecting from raindrops, and the angle between the incoming and reflected rays is theta equals 4r minus 2i, where the angle of incidence I and refraction r are related by Snell's law, which is sine of I equals n sine of r, where n is the index of refraction, which for this case is 1.33 because it's air and water. So we are asked to use Rolle's theorem on the interval 0 degrees to 96.6 degrees to check that theta of 0 equals theta of 96.6, and then find a point C on the interval such that theta prime of C is equal to 0. And this is just a little drawing of a rainbow and the diagram that kind of shows the geometry and everything like that that's involved that kind of develops Snell's law. So let's take a look at this problem. So we need to look at I is equal to 0 degrees. So when we plug that in, we have sine of 0 degrees equals 1.33 sine of r. And then we have 0 equals 1.33 sine of r, and that implies that r equals 0. So when we plug that into theta, we have theta of 0 equals 4 of 0 minus 2 of 0, which is 0. So now let's rearrange Snell's law to test the right endpoint, or 96.6 degrees. So we have sine of I equals n sine of r. Then we can rearrange that. And then we have sine of r equals sine of I over n. We have r equals inverse sine of I over n. So let's plug in theta of 96.6 degrees and this value for r that we just found too, and that gives us 4 of inverse sine of 96.6 degrees all over 1.33 minus 2 of 96.6 degrees. So this is going to give us a value that's going to be equal to 0 like we found for our left endpoint, or if we were to call the interval a, b for a at 0 degrees. But we need to understand some trig substitutions that get us to that point. So we are going to use trig substitutions here. Substitutions. So if we let theta equal to 0, then 0 equals 4r minus 2I, and then we have r equals I over 2, and then sine of I equals n sine, we plug in our new r, I over 2. So now for here, we are going to use a double angle identity. And that identity is that sine of I is going to be equal to 2 sine of I over 2 cosine of I over 2. Excuse me, this is for the wrong one. We're going to use it for this one right here. So that gives us, plug that in here and then bring it down here. That gives us 2 sine I over 2 cosine I over 2 equals n sine of I over 2. And we have 2 cosine I over 2 equals n. And then we have cosine of I over 2 equals n over 2. And then that gives us I equals 2 inverse cosine of 1.33 over 2. And this is where 96.6 degrees comes from. So using all this, we can substitute I over 2 up here all the way back into our equation up here. Well, we'll substitute it here. There we go. And then it'll come down here, and that gives us theta of 96.6 degrees equals 4 times 96.6 degrees over 2 minus 2 of 96.6 degrees, and that gives us 2 of 96.6 degrees minus 2 of 96.6 degrees, which is 0. So theta of 0 equals theta of 0 degrees equals theta of 96.6 degrees. So this is good. Rolle's theorem is verified. That's the first part that the problem was asking for. So now let's find theta prime of I. So theta prime of I equals 4 dr over di minus 2. And also for Snell's law, when we take the derivative of it, we get cosine of I equals in cosine of r times dr over di. Since we're differentiating with respect to I, then we can rearrange here. Then we have dr over di equals cosine of I over n cosine of r. So now theta prime of I equals 4 times cosine of I over n cosine r minus 2, and then 2 equals 4 times cosine of I over n cosine r. Let's plug in theta prime of c equals 0. Okay, sorry, I skipped a step. We're just plugging in theta prime c equals 0 here, and then we rearrange here, and then we come down here. So this is supposed to be c. There we go. So now we have 2 cosine of c equals n cosine of r. And then we have, if we square both sides, we have 4 cosine squared of c, which equals n squared cosine squared of r, which the reason that we're squaring is we can use a trig identity, which is cosine squared of theta equals 1 minus sine squared theta. We can also use it right here too. So that gives us 4 of 1 minus sine squared of c, which equals n squared 1 minus sine squared of r. And now we have 4 minus 4 sine squared of c equals n squared minus sine squared of c. So we have 4 minus n squared equals 3 sine squared of c. Then we solve for c. We have sine of c equals the square root of 4 minus n squared over 3. And now we can isolate c. And that's going to be inverse of sine of this square root and that is approximately 59.6 degrees. And that is the f prime of c that is on this interval that we verified using Rolle's theorem for rainbows and light reflecting. Now that may have been kind of a lot involved with this problem. So if there's anything you have questions about with how this was worked, please post a comment below and I will be glad to answer that for you. Now for problem 4, we are asked to find a point C that satisfies the mean value theorem of the function y equals inverse tangent of 2x on the interval 0 to pi half, and the function y equals x over x plus 4 on the interval 0, 7. So let's work this one out. So for the first one, let's find y prime. Or remember that we have the mean value theorem, y prime of c equals y of b minus y of a over b minus a. So what we have is inverse tangent of 2 times pi halves minus inverse tangent 2 times 0 all over pi halves minus 0. That gives us inverse tangent of pi all over pi halves, and that is approximately 0.803813. So we have y prime equals d over dx of 2x times 1 over 2x squared plus 1, because if you remember inverse tangent, the derivative of it was 1 over x squared plus 1, but we have to do a chain rule here because we don't have x, we have 2x. So that's going to give us 2 times 1 over 4x squared plus 1, which is 2 over 4x squared plus 1. So we plug in our point. We have 0.803813 equals 2, and if we substitute c for x, we have 4c squared plus 1. So now we have 4.803 c squared. We have 4 times this plus 0.803813 equals 2. So c squared equals 2 minus 0.803813 all over 4 times 0.803813. We do a multiplication sign, so this is a little easier to tell what's going on. Let me do this one. Just because when I put that point there, it makes it look like 4.0.803813. So that gives us c equals the square root of, when you plug all that in, it gives you this decimal. So that is 0.609947. Now for part B, we have y prime of c equals 1 over 7 plus 4 minus 0 over 0 plus 4 all over 7 minus 0. And that gives us 7/11 minus 0 over 7, which equals 1 over 11. And then when we do y prime, we have the quotient rule. So we have x plus 4 times 1 minus x of 1 all over x plus 4 squared. And that gives us x plus 4 minus x all over x squared plus 8x plus 16, which gives us 4 over x squared plus 8x plus 16. So we have 1 over 11 equals 4 over c squared plus 8c plus 16, which gives us c squared plus 8c plus 16 equals 44. And then we have c squared plus 8c minus 28 equals 0. Well, what we are going to do, we'll go over here. To write it, we will use the Pythagorean theorem. So we have c equals -8 plus or minus the square root of 8 squared minus 4 times 1 times 28. And that is all over 2 times 1, which is 2. And that's going to eventually, when you write all that out, that's going to give you a value of -8 plus or minus the square root of 184 over 2. And those are the values of c that satisfy the mean value theorem for these. Now on to problem 5. For problem 5, we are going to use L'Hopital's rule to evaluate the limit as x approaches 1 of x cubed plus 2x minus 3, all divided by log base 10 of x. Okay, so for this one, when we plug in x equals 1, we have 1 cubed plus 2 times 1 minus 3 all over log base 10 of 1. And that gives us 1 plus 2 minus 3 over 0, which gives us 3 minus 3 over 0, which is 0 over 0. And that is indeterminate form. So we need to use L'Hopital's rule for this to evaluate this limit. So we have the limit as x approaches 1, so we will do the derivative of the top function, and that's going to be 3x squared plus 2, and then the derivative of log base 10 of x. Well, if you remember, the derivative of the logarithmic function was 1 over the natural log of the base times x. So that's going to give us 1 over ln 10 times x, which if we rearrange here, that's going to be 3. Well, we'll go on and plug in the limit 1 plus 2 over 1 over ln 10 times 1. And that gives us 5 over 1 over ln 10, and then when you rearrange things, that gives you 5 ln 10. And that is the limit of this function using L'Hopital's rule. Now for problem 6, we are going to sketch the graph of the function f of x equals x raised to the 2/3 plus x to the third. Okay, so for this problem, to sketch the graph, we need to determine intercepts, critical points, monotonicity, points of inflection, and concavity. So let's start by determining the x and y intercepts. So for the x-intercept, we are going to set f of x equal to 0. So that gives us 0 equals x raised to the 2/3 plus x to the third. And then if we factor out an x to the 2/3, that gives us 1 plus x to the 7/3. So we divide that x to the 2/3, that leaves us 1 plus x to the 7/3. And then we have -1 equals x to the 7/3. And then we solve for x. We are going to take x to the 3/7, or x, the cube root of -1 to the 7th, which gives us the cube root of -1, which is -1. So our x-intercept is -1, 0. And now for our y-intercept, we are going to set x equal to 0. So that gives us f of x equals 0 2/3 plus 0 raised to the third, which is 0. So our y-intercept is going to be 0, 0. Now let's find f prime of x. That's going to be 2/3 x to the -1/3 plus 3x squared. So now let's set f prime of x equal to 0. So we have 0 equals 2/3 x to the -1/3 plus 3x squared. Then we rearrange. 2/3 x to the -1/3. Then we divide by the -1/3. That gives us x to the 7/3 equals -2/9, because we divide by the -3. Then we have x equals -2/9 raised to the 3/7, which is approximately -0.525. So this is a critical point, but we need to plug this back into f of x to determine the respective y-coordinate. So when we plug in f of negative 0.525. That gives us negative 0.525 to the 2/3 plus negative 0.525 to the 3rd. And that gives us approximately 0.506. So a critical point is negative 0.525, 0.506. And also notice that 0, 0 is a critical point. Because if you look at our f prime of x, when you set it equal to 0, you could plug in 0 into both the x terms, and it wouldn't give you 0, but it would be undefined because you have x raised to the negative 1/3, so you would have 2 over 0 plus 0. So we have our 2 critical points there. So now let's make a table here. Let's make a table. So we have from negative infinity to negative 0.525. Then we also have from negative 0.525 to 0. We don't want to include that point in the interval 0 because it's undefined. So let's determine our monotonicity. So let's choose a point on the first interval, the one on the left, and a point we can use is -1. So let's plug in f prime of -1. F prime of -1 equals 2/3 times -1 to the -1/3 plus 3 times -1 squared. And that gives us 7/3. So we are increasing on this interval. Now let's plug in f prime of -0.1. That gives us f prime of -0.1. And I know you understand what to do here. We'll just plug it into the equation, and that gives us -1.406. So we have a negative value, so we are decreasing on this interval. Now let's plug in f prime of 1, f prime of 1. So f prime of 1 equals 2/3 times 1 to -1/3 plus 3 times 1 squared. And that gives us 11/3. So we are increasing at this point. So we can determine from this that the point -0.525 to 0.506 is a local max. Now, notice that our point 0, 0 is undefined, so we technically, if we were looking at this behavior, we would think that it's a local min, but since this point is undefined, we need to kind of wait on claiming that, because this point could be an asymptote or it could be a cusp, and we'll have to figure that out when we sketch the graph. So now let's find f double prime of x. So f double prime of x is negative 2 over 9 times x to the negative 4/3 plus 6x. So now let's set f over prime of x equals 0. So we have 0 equals negative 2 over 9 x to the negative 4/3 plus 6x. And we're going to have the same condition here. X equals 0 is undefined. So 0, 0, we'll just say it's undefined and go from there. It'll still be a point that we'll look at on the interval, but it's probably not going to be a point of inflection. So we'll see. But now let's solve the equation and find another x value. So when we rearrange, we have negative 6x equals negative 2 over 9 x to the negative 4/3. And then we have negative 6x negative 7/3 equals, or 7/3 equals negative 2 over 9. And then we have x to the 7/3 equals 1 over 27. And then we have 1 over 27 to the 3/7, which is approximately 0.243. So let's find the respective y-coordinate. So if we plug in f of 0.243, that gives us 0.243 to the 2/3 plus 0.243 to the third, and that's approximately 0.404. So 0.243 and 0.404 is a point of inflection, or at least it should be. We'll obviously make a table and figure out the shape of the graph, and determine if that's true. So let's make tables again, or let's make a table. So we have from negative infinity to 0. Then we have from 0 to 0.243. Then we have from 0.243 to infinity. Okay, so let's plug in a point on the first interval in the left. So let's plug in f double prime of -1. So f double prime of -1 equals -2 over 9, -1, -4/3 plus 6 times -1. And that gives -56 over 9. So this interval is concave down. And now let's do f double prime of 0.1. So f double prime of 0.1, you plug everything in and you get approximately -4.188. So we are also concave down. now let's do f double prime of 1. So f double prime of 1, when you plug everything in, that gives you 52 over 9. So we are concave up. So since we stay concave down, the point 0, 0 is not a point of inflection because our concavity doesn't change. But our point 0.243, 0.404 is a point of inflection because we change from concave up to concave down. So we have everything that we need. So now let's sketch our graph. We are ready to make this thing. So let's sketch our graph here. And from the points, we have our y-axis, and then we have our x-axis. From our points, we might just want to do this in intervals of 1, 1, -1, -1. So we have our point 0, 0. And then this is our x-intercept. And then we have, this was our point negative 0.525 to 0.506, kind of about right there. And then we have our point 0.243, 0.404. So that would go 0.2, 0.4, somewhere about right here. Okay, let's look at our monotonicity. So we are increasing up to our critical point, and we are concave down on that interval up to 0. So we are probably going to go, I'll move the -1 over here. Start like this, and then after this point we were decreasing, but we're still concave down. And then from this point up to our point of inflection, we were concave down and increasing. So we'll go something like that. And then we were concave up after this point and increasing. So let's see if I can sketch this a little better. Because from sketching this graph, you're going to find that this point right here is a cusp because of the behavior of it. So yeah, this is our graph. And that explains why the point 0 was undefined, because it is a cusp. So this is our sketched graph for problem 6. Now we will work problem number 7. So for problem number 7, we are asked to suppose a rectangular train car is being designed to carry 100 people with a required volume of at least 200 meters cubed. And the car is also required to be at least 25 meters long. And we need to determine the optimal dimensions of the train car to minimize the material required to build it. Okay, so this is a applied optimization problem. So this train car is going to be in a rectangular shape. So if you look at the little sketch that we have here, we have the length, the width, and the height of the train car. So our volume is going to be equal to length times width times height, which is 200 meters cubed. And we are going to start our solution here. So the material will be based on the surface area So for the surface area, you have to look at the surface areas of all the faces of the train car. So if we were looking at like those in the diagram there, the one with the door, we would have the height times the width. And since this is a rectangular shaped car, we would also have the same surface area on the opposite side of it. And then for the top face, we would have the length times the width, and same for the bottom, and so on and so forth. So all the surface areas we need to consider for this car is going to be 2 times length times width plus length times height plus width times height, because we have all three of the areas and we have them occurring twice since this is a six-faced figure. So we have 200, and we know the length, so we have 25 times width times height. So our width times height is equal to 200 over 25, or 8. And then we can rearrange this to solve for one of the variables here. Our height is going to be equal to 8 over the width. So now our surface area width as the variable is going to be 2 times 25 times width plus 25 times 8 over W plus 8. So if we take the derivative of our surface area equation we have here, we get 2 times 25 minus 200 over W squared, which gives us 50 minus 400 over W squared. So that is our derivative of our surface area equation with respect to the width. So now let's set that equation equal to 0. So 0 equals 50 minus 400 over width squared. Then we rearrange over width squared. Then we have our width squared equals 400 over 50, which equals 8. And then we have our width equals the square root of 8, which equals 2 square root of 2. And now let's plug this back in to figure out h. So h equals 8 over 2 square root of 2, which coincidentally gives us 2 square root of 2. And these are both in meters. So this is our width and our height that we need. So the optimal dimensions for the train car dimensions are 25 meters by 2 square root of 2 meters by 2 square root of 2 meters. And this is using applied optimization. With our surface area equation, we were able to optimize this to minimize the amount of material we need to build this train car. Now for our last problem, we are going to use Newton's method to find the first 3 approximations of e of x plus ln x squared with an initial guess of x0 equals 1. Okay, so let's work this problem out. So Recall that Newton's method, we have xn plus 1 equals x of n plus f of x of n over f prime x of n. Sorry, this is supposed to be minus. So let's find f prime of x. That's going to be e of x plus 2x over x squared, which is equal to e of x plus 2 over x. So now let's find x of 1. We plug in 1, we have 1 minus e to the 1 plus ln of 1 over e to the 1 plus 2 over 1, which gives us approximately 0.423883. Okay, so there's our x of 1. Now let's find x of 2. We have 0.423 minus e to the 0.423883 plus ln of 0.423 all over e 0.423. Keep forgetting the 2 for some reason. 883 plus 2 over 0.423883, and that gives us approximately 0.454096. And then for x of 3, well, I think you can understand what to do here. You're just plugging it in again, and that gives approximately 0.454789. And that is the value we were looking for because this problem wanted us to go for the first 3 approximations using Newton's method. Now the last topic that's going to be covered in Calculus 1 is the integral. So in the previous sections, we looked at differentiation or rates of change, which in graphical terms is slope of functions. So the integral focuses on the opposite of this. Which specifically is the area of a graph of function or function. So the first topic that we will look at for integrals is approximating and computing area. So suppose we have a graph of water flowing from a river. And the graph looks something like this. We will have our flow rate, gallons per minute. Then we have our time, which is minutes. Sorry, this is actually going to be volume, which is gallons, and then we have our minutes. So 1, 2, 3, 4, 5. And then we have our x-axis. 1, 2, 3, 4, 5, 6. And then our graph goes something like this. So, sorry, this is actually supposed to be, that was right. This is supposed to be Q, gallons per minute. So the area tells us how many gallons of water flowed over this time. So if we were to put this in equation form, we would say that the water delivered equals flow rate times time. Or if we were to look at our graph, we would have Q delta T. We were basically multiplying our units of our y-axis times the units of our x-axis. So we have gallons per minute times minute. So we can use geometry such as rectangles to approximate the area of the graph. So we can do this by using 3 methods of rectangle area approximation. We will go over what those three rules are. So we are going to assume f is continuous and positive. So let's define n to be the number of equal distance rectangles on an interval AB, or from A to B, of f. So one method we can use is write endpoint approximation So if we have our graph, then let's say the graph is going something like this. Then we have our rectangles. Here, let's see if we can draw this again. Then we can make another one here, and another one here. Oops. Here, let's try to make this. Here, let's actually just draw up the rectangles here, and then we'll make a graph going over it. And we'll go like this. I know this may not exactly be equal distance, but this is just an illustration to help you understand the idea. So we'll go something like this. And then we're looking at all the right endpoints, which are on the graph. So we will call this point f of x1, and this is the point x1, x2, and we are on the interval from A to B. We go so on and so forth. So for the right endpoint approximation, we'll define it Rn equals delta x times f of x1 plus f of x2 plus all the way up to f of xn. Okay, so that's one of the three methods that we can use. We can also use left endpoint approximation. So if we draw out a graph, draw out our rectangles, let's see, we'll draw them something like this. And our graph is going to go something like this. So we look at all the left endpoints that we have. Then we will call this point x naught, then f of x naught. Then we have f of x1 and so on and so forth. This point will be x1, x2, so on and so forth up to n minus 1. So our left endpoint approximation, L of n, is equal to delta x times f of x naught plus f of x1 plus f of x2 plus so on and so forth up to f of x n minus 1. Okay, now midpoint approximation. This is the third method you can use. So if we were to make a graph depicting this, it would be something like this. rectangles. And then the graph will go something like this. So we look at all the midpoints of the rectangles. So we call this our interval A to B. Then we look at the midpoints here. So we have x0 plus x1 over 2. And then for this midpoint, we have x1 plus x2 over 2, so on and so forth. And then our top points, respective y coordinates, we have f of x0 plus x1 over 2. And for this one, we have f of x1 plus x2 over 2. So our midpoint approximation, m of n, is going to be equal to delta x times f of x0 plus x1 over 2 plus f of x1 plus x2 over 2 plus so on and so forth up to f of xn minus 1 plus xn over 2. And those are the three approximations you can use for rectangles. Now we can write these in a summation form. This is just an easier and more general way to describe these. So if we were to put these in summation form, we would have, for right-hand approximation, it would be delta x times the sum as j equals 0 to, or j equals 1 to n of f of xj. Then for left-hand approximation, we have delta x times the sum as j equals 0 to n minus 1 of f of xj. And then for midpoint, we have delta x times the sum j equals 0 to n minus 1 f of xj plus xj plus 1 over 2. Now, all of these approximations will approach the same limit eventually. So there's a theorem revolving around this. So the theorem is that the limit of the right endpoint approximation as n approaches infinity equals the limit as n approaches infinity of the left endpoints, which equals the limit as n approaches infinity of the midpoints, which equals L, where L is the area under the graph where f of x is strictly greater than or equal to 0 over the interval from a to b. That's pretty much all there is to understand about computing area using geometry such as rectangles. So now we'll change colors here, and we will start talking about the definite integral. So continuing on what was just discussed, we can develop a Riemann sum for finding area. So say we have a partition P of size n. So n is a choice of points that divides the interval from A to B into n subintervals, and then P is going to be A equals x naught, which is less than x1, which is less than x of 2, so on and so forth, which is all less than x of n, which is going to be equal to b. And then we have sample points, which is C equals the set of C1, so on and so forth, up to Cn. And Ci belongs to the subinterval of xi minus 1 to xi for all I that is equal to 1 up to n. So here's kind of a little line that represents this. So say we have our x of naught, which is A, then we have our point C1, then we have x of 1, and a point in between called C2, then you have xi minus 1, then say the point Ci is here, then you have x of I, and then this interval between them is called delta xi, and so on and so forth. You could have another point, then another one here, we'll call this one Cn, all the way up to xn equals b. So there's a theorem which is the max of links delta xi of P is denoted like this is supposed to be the norm, not theorem. The norm, which is the max links of delta xi of P, is denoted by these double straight lines with P inside. So this gives us a definition for a new way of finding area, which is called the integral. So, what is an integral, or more specifically, what the title of this section is, the definite integral? So here's a definition of it. So, the definite integral of f over the interval from a to b, which is denoted by an integral sign, which this is the integral sign, is the limit of the Riemann sums that we just discussed. So the definite integral from a to b, this is normally how you write an integral. You would write the symbol, and then at the bottom you put your lower limit, and then at the top you put your upper limit. So you have from a to b of the function f of x with respect to your differential dx. That's equal to the limit of the norm of, as the norm of p approaches 0, of the Riemann sums of f, p, and c, which is equal to, again, the limit as the norm of p approaches 0 of the sum from I equals 1 to n of f of ci delta xi. This is essentially what the definite integral is. And an important definition to remember for it. So when the limit exists, f is said to be differential or integrable, over the interval from a to b. So if you reverse the limits of integration, and this is assuming when a is strictly less than b, you have the integral from a to b of f of x dx equals negative the integral from b to a of f of x dx. Box drawn right here. There we go. So another thing to note is that an integral can have both a positive and a negative value. So let's say we have this graph right here, our y-axis and our x-axis. Then the graph is going something like this. So if you were to do the integral of this area right here, this area would be positive. But if you were to do this area right here, this area would be negative. So the area for this graph would be equal to the area above the x-axis minus the area below the x-axis. So let's suppose we have a graph that is as follows. So the graph, it goes, let's draw out our plot here. We have our y-axis and our x-axis, and we're on the points 1, 2, 3, 4. And then we have one line going here, another going here. So this is, we'll call this the upper bound. And we'll call this the lower bound. And we say m and m, lowercase m and capital M, represent the upper and lower bounds, respectively. Then we have the slope m times b minus a is less than the integral from a to b of f of x dx, which is less than or equal to capital M of b minus a, where m is less than or equal to f of x, which is less than or equal to m, and x is in the interval a to b. And I believe I have this wrong, because capital M represents the upper and lowercase m represents the lower. That would make more sense with this definition. Because basically what's happening in this definition is you're saying that the area of the two graphs, which is equal to m times b minus a, which would kind of be like the area, it's kind of saying x times the interval. For the lower is less than if we were to do the integral of the upper bound graph, which is less than the area of the upper graph. Now we will look at the indefinite integral. So compared to the definite integral, an indefinite integral is not bounded on an intervals such as from A to B, and represents a general antiderivative of a function So I just mentioned antiderivative. This is an important word to remember, and we will look at a little more formal definition of what this is. So the definition of an antiderivative it is a function which is often denoted by capital F, or a function capital F is an antiderivative of a function f on an open interval AB if f prime of x equals f of x for all x in the open interval A to B. So this leads to a theorem about the general antiderivative. So the theorem is that let y equal capital F of x be an antiderivative of y equals lowercase f of x on the open interval A to B. So then every other antiderivative on the open interval A to B is of the form y equals capital F of x plus c for some constant c. And the notation for this is the integral of f of x d of x equals capital F of x plus c. And in other words, this means that f prime of x equals f of x. So now let's change colors here. And now we will look at a table of some general definite and indefinite rules / theorems. And I'm going to copy and paste that table on here. And here's the table with all the rules, or just a lot of the rules and theorems for antiderivatives. So for the power rule, when you integrate a function raised to a power, it equals the power raised, or the power plus 1 divided by the power minus 1 plus c when n is not equal to 1. Then you have the sum rule. It's kind of similar to the sum rule for derivatives. Then you have the multiples rule, which is basically saying if you have a constant times a function, you can just multiply that constant after you integrate the function. Then we have the constant rule. So if you have a constant in an integral, and this is a definite integral because you have from a to b, this is equal to constant times the bound subtracted, with the upper bound b subtracted from the lower bound a. For 1 over x, it gives you the natural log of the absolute value of x plus a constant. This is an indefinite integral. Then you have e of x. So when you integrate e of x, you have e of x, but you also have a constant. This is if it's an indefinite integral. Then if you have the exponential function raised to a function times some constant k, then that gives you 1 over k times exponential, and then again your constant c. But this is again if it's an indefinite integral. Then these are all the trigonometric integrals, so you can just kind of look at them here. I'm not going to explain what all of them are. However, I will look at the last two that we have, sine k of x and cosine k of x. So the antiderivative of those, for sine k of x, you multiply by 1 over k because it's just saying whatever your function in the sine is times a constant. When you integrate it, the integral is negative 1 over k, and then of course cosine, because you know the derivative of sine is cosine, but the antiderivative of sine is negative cosine because you have the sign flipping, and it's a similar thing for cosine. Then you have inverse trigonometric functions, and you can see what they are here. And then you have the integral of b of x, which is, this is just an exponential function with a different base. And it's equal to the exponential function over the natural log of the base plus c. Now the next topic we are going to look at is the fundamental theorem of calculus. So, since we have covered differentiation, and integration, which are basically two opposites, you might wonder why study both? Because if you're learning about one thing, why would you want to learn basically the opposite of it? And that is an interesting question to ask. And that is where the fundamental theorem of calculus comes into play. Try to make this guy look a little more confused than. So this is because the fundamental theorem of calculus this is because of the fundamental theorem of calculus, which is basically the whole reason why calculus is important to study. Or at least that's what this theorem is intending to tell us. So we have two parts to look at for it. So let's change colors here. We will look at the first part of the fundamental theorem of calculus. So for the first part, the theorem is assume that f is continuous on the interval from a to b. So if f is an antiderivative, well, let's call it capital F, is an antiderivative of lowercase f on the interval a to b, then the integral from a to b of f of x d of x equals capital F of a minus, or b, minus capital F of a. And this is essentially the first part of the fundamental theorem of calculus. It's essentially saying that the definite integral of lowercase f is equal to the antiderivatives with the endpoints plugged in. So this essentially shows us that the definite integral and antiderivative are related and are the same when evaluated. Okay, so that's the first part of the fundamental theorem of calculus. Now we'll change colors and we'll look at the next part of the theorem. And that part tells us that if we assume that f is continuous on an open interval, let's call this interval I, and let A be a point in the interval I. So then the area function which is a of x where A is the area, equals the definite integral from A to X of f of t dt is an antiderivative of f on I and this is an important function to remember, so let's box it. So that is a prime of x equals f of x. Or if we were to put it just in a simple function, equivalently, we would have d over dx of the definite integral ax f of t dt equals f of x. So furthermore, a of x satisfies the initial condition a of a equals 0. So this part shows us that the antiderivative and integral are also the same when evaluated, just with an additional condition that one point, which in this case is the lower bound, yields 0. And that's essentially both parts of the fundamental theorem of calculus summed up simply. So now let's get our green pen here. So after seeing both parts of the fundamental theorem of calculus, you might wonder, why is this so fundamental to this course and this topic? And what does it mean? Besides what you see in the theorems, what is maybe a more easier way to understand it? So let's use an image of a pool to visualize it. So here is a little in-ground pool that I drew from my notes that I am copying over here that we will use to understand the fundamental theorem of calculus. So let's say the pool holds 20,000 gallons of water. And the base has, or the hose, excuse me, the hose has a flow rate of 5 GPM, or gallons per minute. So you could use geometry and then mark a line on the pool to know when it is filled. It is filled. Or you could do math to find that if you divide 20,000 gallons over the 5 gallons per minute, well, the gallons will cancel out, and that will give you 4,000 minutes. So that means that you could wait 4,000 minutes and the pool will be filled. So either one are the same thing. So whether you want to make your mark in the pool of where 20,000 gallons is when you do geometry, because this is just a simple rectangular in-ground pool, or whether you turn on your hose, since you know how much water it pumps out, and wait 4,000 minutes, you'll get the same result either way. And if we were to put this in the fundamental theorem of calculus form, we could write it as the definite integral from 0 to 4,000 5 dt, or 5t, and that's 5 dt equals 5 times 4,000 minus 5 times 0, and that gives us our 20,000 gallons. So using this visualization, this is why this is so fundamental. It shows that the derivative or the rate and the antiderivative which is essentially the total, work together. And by understanding this and knowing this fundamental theorem, this shows that studying change is useful. And this is why calculus is such an important math to study, because whether you're looking at the change of something or whether you're looking at the total of something, you can relate it to that in a way and find a way to design something, such as designing this pool. Now the next topic that we are going to study is net change. So this topic builds off of the fundamental theorem of calculus. So a theorem relating to this is the net change in ST over an interval from T1 to T2 is given by the interval, or by the integral, the definite integral from T1 to T2 of S prime of T dt equals S of T2 minus S of T1. And what this term is describing is the integral of the rate of change, and then this term is the net change over the interval T1 to T2. So this is useful in an area like physics or accounting. And these are some examples of doing so, or how they relate to them. So if we were to look at displacement during an interval from T1 to T2, we'd say that's equal to the integral from T1 to T2 of our velocity with respect to dt. Or if we were to look at the distance traveled during the interval T1 to T2, we would say that it's equal to the integral from T1 to T2 of the absolute value of v of t with respect to dt. Or let's say we are going to look at the cost of increasing production from A units to B units. That'll be integral, or that'll be equal to the integral from A to B of C prime of x, the cost, the derivative of the cost with respect to dx. And these are just a few examples. There are obviously a lot of other applications of net change, but these are just some of the more common ones that you would often see this being related to. So it's pretty neat. Now we will change colors and we will take a look at the substitution method. Substitution method. So integration is often more difficult than differentiation. So many antiderivatives cannot be expressed in simple functions so there is one technique that can be used to solve some more challenging integrals. And this technique that we are going to look at is called the substitution method. So the substitution method, it is essentially the chain rule in reverse. And the theorem about the substitution method states that if f prime of x equals f of x, then the integral of f of u of x times u prime of x dx equals uppercase F u of x plus c. So basically what's happening is we're substituting another function called u in for whatever our original function was. And that's what I'm going to write here. Essentially, what you do is choose a function and in this case it's u of x. That's the most common thing used for this method, and let it make a harder function simpler. So this works by looking at the differentials, so if we were to look at the differentials, we would say that du would be equal to du over dx. Well, the dx's cancel, and that gives us du, and also du and dx are related by du equals u prime of x d of x. This is an important formula to remember. So for definite integrals, say we have a to b of f of u of x times u prime of x dx, that is equal to the integral of u of a to u of b f of u of du. So let's look at an example of this. So let's evaluate the integral 8 raised to the 4t of dt. So what we are going to do is we are going to let u be equal to 4t, and then we have du equals 4 of dt, and then we have dt equals 1 over 4 du, so we plug that in. We have 1 over 4 8u du, which equals 1 over 4. We can just take that constant out. 8u du. That gives us 1 over 4. When we integrate, the integral of 8u over ln of 8 plus c. And when we multiply everything, that gives us 8 raised to the 4t, because we'll substitute our u equals 4t back in, divided by 4 ln of 8 plus c over 4. Or sometimes they just leave it as the constant c, because when you multiply an unknown constant c by another constant, it's just assumed to be another constant since it's not defined. But I'm going to leave it as c over 4 just because I like to think of them as different constants, but that varies a lot. Now we'll change colors here and look at the last topic for Calculus 1, and that is exponential growth and decay. So this is the last topic for Calculus 1. So we are almost done with the lectures for this. And then, of course, there will still be some example problems that will work for the integral, since I kind of have this course split up into the 4 parts. But then after that, this course will be done. So we will look at some applications of the exponential function. So let's consider a quantity called p of t that depends exponentially on time. So we will say that P of t equals P naught e raised to the kt. And if, this is with the assumption if k is greater than 0, then P of t grows exponentially, or this is with the condition, and k then k is called the growth constant. So this function gives us a solution, solution to y prime equals ky, which that is a differential equation. So the theorem for this is that if y is a differentiable function satisfying the differential equation y prime equals ky, then y of t equals P naught e raised to the kt, where P naught is the initial value P naught equals y of 0. So let's look at the proof of this theorem. So we are going to let y prime equal ky. So now let's compute the derivative of y times e to the negative kt. So we have d over dt y times e to the negative kt. That equals y prime times e negative kt, which equals k e to the negative kt, or excuse me, it's supposed to be y prime e to the negative kt because we're doing the product rule here, and then it's minus k e to the negative kt times y. And then we have ky times e to the negative kt minus k e to the negative kty, and you'll notice that that equals 0. So yt e to the negative kt equals, let's say, P naught, where P naught is a constant. So therefore, y of t equals p naught e raised to the kt as desired. And this proof just gives an airtight logic behind this theorem that it is a solution of the differential equation. And we can find that by taking the derivative and showing that the derivative is equal to 0, which means that it must be equal to some constant, and we'll define it as p naught in this case. So exponential growths have a property called doubling time, which is where p of t doubles and exponentially decaying functions have a property called half-life. And half-life is where p of t achieves half its initial value. So these are how they are described. The doubling time for an exponential function that's growing is ln of 2 over k. And then for half-life, it is the same thing, except this is for an exponentially decaying function. It equals ln of 2 over k. So carbon dating which is basically dating organisms from carbon inside them is an application of exponential decay. So, carbon in the atmosphere which is C12 is non-radioactive and radioactive carbon, which is C14, decays, trying to erase that to fix that E, decays into nitrogen. So the ratio between C14 to C 12 is approximately and this ratio is described or notated using RATM equals 10 to the negative 12. So the decay constant of C14 is 0.000121 in units of year to the negative 1. So the ratio of C14 to C12 after t years equals RATM raised to the negative 0.000121 times t. So since an organism that is no longer alive doesn't replenish carbon, this equation can be used to date it and figure out how old it is. So it's a pretty neat application of carbon dating. Of course, I know there's other methods of dating, and I know that some of them may be more accurate than this, but it's still a neat little topic to study, and it still can be useful in some areas. But exponential growth and decay are useful in financial calculations too. So one such application is compound interest. So, well, there we go. So compound interest, basically, if we have P0 dollars are deposited into an account that is earning interest at an annual rate, which is notated by R, compounded M times yearly, then the value of the account after t years is P of t equals P0 times 1 plus R over M raised to the MT. And notice that 1 plus r over m is the yearly multiplier. And we can develop another related interest equation by using the limits of e and e to the x. And those limits are e equals the limit as n approaches infinity of 1 plus 1 over n raised to the n, and e of x equals the limit as n approaches infinity of 1 plus x over n raised to the n for all x. And these are some important formulas to remember. So notice that if we take the limit as m approaches infinity of 1 plus r over m raised to the m, we get e raised to the r. So this develops a new formula. And that formula is continuously compounded interest. And that formula is P of t equals P naught times ERT. And another financial application is present values. And what this does is it compares payments made at different times. So the present value which we will notate with PV of P dollars received after time t is P e to the negative RT. So the present value of an income stream if the interest rate is R, the present value of an income stream paying out R of T dollars per year continuously for t years is the present value equals the integral from 0 to t of r of t e negative rt dt. Now we'll work some example problems for the last part of Calculus 1, the integral. So the first problem we are asked to work is to approximate the area of ln of the square root of x using R4 and L4 on the interval 2 to 5. So R4 and L4, they represent right and left endpoints of rectangles. So that's the approximation we are going to use for this problem. So let's start working this out. So first we need to find our delta x, the distance between the endpoints. So the 4 in R4 and L4, that represents the number of points we're going to use, and our interval is 5 minus 2. And then we have our number of points, so our delta x is going to be 3 over 4. So for R4, our right endpoints will be 11 over 4, 14 over 4, or 7 halves, 17 over 4, and 20 over 4, or 5. So where are these points coming from? Well, if you remember the formula for the right endpoints of a rectangle, you will go from the first point, which is 2 on this interval, and then our delta x is 3 over 4, so 2 is 8 over 4, and then we add 3 over 4, and that's our first right endpoint. And then we're doing 4 points, so we just keep adding 3 over 4s to get these points. So that gives us R4 equals our delta x, 3 over 4, times ln of the square root of 11 fourths plus ln square root of 7 halves plus ln square root of 17 fourths plus ln square root of 5. And these are all our right endpoints for this approximation. We'll just leave it in this form because you can plug it into a calculator if you're curious what like a decimal or number approximation of that would be. So for L of 4, our left endpoints will be 8 over 4, because for left endpoints we start at the point on our interval. Then 11 over 4, then 14 over 4, or 7 halves, and then 17 over 4. So L of 4 is going to be equal to 3 over 4 times ln square root of 2 plus ln square root of 11 fourths plus ln square root of 7 halves plus ln square root of 17 fourths. And these are our left endpoints for this approximation using 4 endpoints. Now for our second problem, we are asked to find the limit as n approaches infinity of m of n, where f of x equals x squared on the interval 6 to 8. So what we are doing in this problem, we are evaluating the limit of the midpoints of using rectangles of this function to approximate the area on the interval from 6 to 8. And if you remember, this was one of the theorems that we discussed, that the limit as these approach infinity, whether it's left, right, or mid endpoints, they all eventually equal the area under the graph for this given interval. And that's what we're going to find when we do this. So let's find our delta x, and we have 8 minus 6, and we don't know how many points we're using, so we'll just leave it as n. So our delta x is 2 over n. So if you recall, the midpoint formula was delta x, and if we were to put it in summation form, because that's what we want to focus for this specific problem, we would have from j equals 0 to n minus 1 of f of xj plus xj minus or plus 1 over 2. So we are going to substitute x of j to be equal to a plus j delta x, because basically what this formula is showing is kind of accounting for when we take our delta x into account as j changes for each respective point, we can just substitute this in for x to find a more general formula. So this is going to be equal to delta x times the sum of j equals 0 of n minus 1 of f of a plus j delta x. And then for our j plus 1, we are just going to have a plus, we just have j plus 1 instead of j delta x. And this is all divided by 2. So now we have delta x in the sum, j approaches 0 to n minus 1 of f of 2a plus 2j plus 1 delta x over 2, because the way we get to this point is you will notice that when you add the a's and the j's together, that you can just put it in a more simplified formula like this. And then we have delta x, the sum is j equals 0 to n minus 1 of f of a plus j plus 1 over 2 delta x, so we just divided everything by 2, and then that gives us delta x, the sum, j approaches 0 to n minus 1 of 6 plus 2j plus 1 over n squared, because what we've done here is we have plugged in our function, which is x squared, and then we also have plugged in our delta x and multiplied it by j plus 1/2, and that's how we get this formula. And a is 6 because a represents the first point on the interval. So what we have now, when you FOIL out this polynomial, I'll just go on and give you what it is FOILed out, and if you want to work it out yourself, you can. But I'm not going to write out all the steps I took to FOIL it out. That gives us 36 plus 24j plus 12 over n plus 4j squared plus 4j plus 1 over n squared. So we can expand this further by distributing the delta x to everything. So then we have the sum from j equals 0 to n minus 1 of 72 over n plus 48j plus 24 over n squared plus 8j squared plus 8j plus 1 over n cubed. So now a good way to look at this is to split these into the terms that have j squared, j, and constants. So if we do such a thing as that, we're still trying to find m of n, and our sum is still the same. But now we have our 8j squared plus 8j plus 1 over n cubed. Then we also have, if we distribute the sum out, this is our j term, because the highest j power we have is just j. And then this is essentially what we're doing. We're splitting it up into the terms that have the highest to lowest power of j. So this term has j to the 1 as the highest power in its term, and then we have the same thing, but we can actually rewrite this last one for the constant. We'll write it as 72 over n times n minus 1, sum of j equals 0 of 1. So now what we are going to do, we are going to use some formulas, because for terms like this, there are actually formulas for like the sum of j squared and sum of j and everything like that, that we can just substitute in to make this easier. So, and I'll give you what some of these are, because I don't believe I covered them in the lecture. So we have n minus 1, n 2n minus 1 over 6 for j squared in this sum. Then we have, for j, we have n times n minus 1 over n. And then for our constant term, we just have n. So we can now write this as m of n. So what we are going to do here, just to kind of clarify this next part, we are going to focus on our highest powers and instead just omit the lower powers that we have. So like in the hj squared plus hj plus 1, we'll just eliminate the hj and the 1 because we're focusing on the highest term here. So what we have now, using these sum formulas, because that's what we're trying to do, we're trying to substitute these formulas in, we have 8 over n cubed times n minus 1 times n 2n minus 1 over 6 plus 48 over n squared times n minus 1 over 2. Then we have 72 over n times n. So now, when we distribute things, we get 4n minus 1 over 6 plus 2n 72. And then we can simplify this further. Now what we're going to do is we're going to distribute everything. So we have 4 times 2n squared minus 3n plus 1, because that's what you get when you FOIL those terms together, over 3, sorry, I forgot to write this. This is 3n squared. 3n squared plus 24n minus 24 over n plus 72. So now what we are going to do with these terms, we're going to take the limit as n approaches infinity. So we have the limit as n approaches infinity of this term minus 3n plus 1 all over 3n squared plus the limit as n approaches infinity of 24n minus 24 over n plus limit as n approaches infinity of 72. So now if you remember when we were covering limits at infinity, you can divide these terms by the highest power of the variable we are finding the limit of, which is n, and then evaluate the limit of that as it approaches infinity. So this brings us to the limit as n approaches infinity of 4 times 2 minus 3 over n plus 1 over n squared, because we're dividing by n squared for all the terms here, over 3, plus the limit as n approaches infinity of 24 minus 24 over n over 1, and then this one is just 72 because we don't have an n term in there. And then what's going to happen is as these fractions right here approach infinity, they're basically going to go to 0, so we'll treat them as such. So that leaves us with 4 times 2 minus 0 plus 0 over 3 plus 24 plus 72. And that gives us 8 thirds plus 96, which is 8 thirds plus 288 thirds, which is 296 thirds. And that is the area under this graph using midpoints of rectangles, but evaluating it as the limit approaches infinity. And by keeping it in a general form and then using some sum formulas and finding the limit at infinity, we have evaluated the area under this graph for this interval. Now for the third problem, we are going to evaluate the indefinite integral of 8 plus x squared over x dx. Okay, so for this problem, we are first going to split the integral up into two fractions. So what we have is we have 8 plus x squared over x. And we can split that up into 8 over x plus x squared over x, which is 8 over x plus x. And then if you remember, we had the sum rule for integrals, so we can write this as the indefinite integral of 8 over x dx plus the integral of x dx. And then what we can do, we can factor out this constant over here, and that leaves us with 1 over x dx. And we still have this integral. Okay, so what we are going to do is, if you remember, this was one of the first one we have. This is one of the integral rules. This is going to be ln of x. So we have 8 ln of the absolute value of x. Sorry, forgot to say absolute value of x. And then for this one, we will just do the power rule. And if you remember, the power rule was x to the n plus 1 over n plus 1. So this is just x, and it's understood to be 1. So we will have n plus 1, which is x squared, divided by 1 plus 1 is 2. And of course, we have our constant c, because this is an indefinite integral. Now for the fourth problem, we are going to find capital F of x if capital F of x equals the integral from pi 6 to theta of secant squared theta d theta, and then we are asked to determine capital F of pi thirds and then capital F prime of pi thirds. Okay, so for this problem, this is kind of following the format of the second part of the fundamental theorem of calculus. So the second part of the fundamental theorem of calculus states that an area function a of x or capital F of x, in this case, is, well, we have f of x equals the integral from pi over 6 to theta of secant squared theta d theta. And if you remember from the integral rules, this is one of the integral rules we can use. So the integral of secant squared theta equals tangent theta. So we have f of x equals tangent theta from, we're going to evaluate it from pi 6 to theta. So we have f of x, then we have f of x equals tangent of theta. We'll plug in the first point, just stays theta. And then we have minus tangent of pi over 6. And this gives us our equation for f of x as tangent of theta minus square root of 3 over 3. Because you remember, pi over 6 was one of those special angles where we kind of know what it is for sine, cosine, and then from there we can figure out tangent, because tangent is sine over cosine. So now let's find f of pi thirds. So all we have to do, we're plugging in pi thirds to tangent here. And of course we have our constant, square root of 3 over 3. And that gives us square root of 3 minus, square root of 3 minus square root of 3 over 3. And then if we wanted to make this one term, just multiply it by 3. We have 3 square root of 3 minus square root of 3 over 3. So there's f of pi thirds. So now we are asked to find capital F prime of pi thirds. Well, capital F prime of x is just equal to our equation that is in the integral, which is secant squared of theta, or in this case, it's going to be secant. We're just going to change the variable to match secant squared of x. So capital F prime of pi thirds equals secant squared of pi thirds, which equals, well, secant is 1 over cosine, and cosine of pi thirds is 1/2, so 1 over 1/2 is going to be 2. Of course, that's going to be squared, which is 4. Now for problem 5, we are going to suppose a patient has a heartbeat that has the equation f of t, and you can see f of t there. I'm not going to read out all those decimals just to save me some breath. And a graph of the function is shown below. And we are asked to determine the total beats the patient's heart does in 10 minutes. Well, okay, I kind of made a little sketch here of the graph to just to show this equation graphed out, and then I thought I would just draw a little heart. We're going to figure out how many heartbeats this guy does in 10 minutes, how many boom, 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 booms it does. So what we're finding is we're just finding the area under this graph from 0 to 10, which would be about right here. So what we are going to do, because we are asked to determine it after 10 minutes, well, we are going to do the integral from 0 to 10 of our equation f of t dt. And that's going to be equal to 0 to 10 of our equation 0.784 t cubed plus 1.70 t squared minus 2.9 t plus 84.44755. And then when we integrate it, that's going to give us negative 0.07848, because we're going to do the power rule here, so that will give us t to the fourth over 4. Then we have 1.17016 t cubed over 3 minus 2.92813. This will be t squared over 2 plus 84.44755t. And of course, this is evaluated from 0 to 10. So what we do at this point is it would just be easier to use a calculator and plug in t equals 10 and t equals 0 to the equation, and subtract. Well, let's call this, because it was called f, lowercase f of t, we'll call this capital F of t. So subtract f of 10 minus f of 0. Because, that's what you do when you evaluate a definite integral like this, and this is the first part of the fundamental theorem of calculus too. And when you plug it all in, because I'm not going to write all that out again, that gives approximately 892 beats that the patient's heart does in 10 minutes. Now for the sixth problem, we are going to evaluate the definite integral from 0 to 1 of 1 over the square root of 1 minus y squared plus e raised to the 7y plus 3 dy. Okay, for this problem, what we are going to do first is we are going to split this into two integrals. We'll just use a sum rule here to make this easier to evaluate. So we will have the integral from 0 to 1 of 1 over square root of 1 minus y squared dy plus the integral from 0 to 1 of e raised to the 7y plus 3 dy. So for the first integral, this is just one of the trig integrals that we covered. It was an inverse trig function. So this one is going to be sine negative 1 of y evaluated from 0 to 1. So that gives us inverse sine of 1 minus inverse sine of 0. And that gives us pi halves minus 0, which gives us pi halves. Now let's take a look at our second integral. So for this one, we will have to use u substitution. So we are going to let u equal 7y plus 3, and then du is going to be equal to 7 dy, so dy is equal to 1 over 7 du. Then we will plug that back in here and then bring it down here. So now we have 1 over 7 from the integral from 0 to 1 of eu du, which then gives us 1 over 7 times eu evaluated from 0 to 1 which now we can plug our u back in. So we have e 7y plus 3 evaluated from 0 to 1, which gives us e to the 10 over 7 minus e to the 3 over 7. So, or thus, we have, when we add our two integrals up, we have pi halves plus e10 minus e raised to the third divided by 7. And that is our answer for problem 6. Now for our last problem, problem 7, we have two parts to this problem. The first part, part A, we are going to determine how much ratio of carbon-14 to carbon-12 is lost by evaluating the integral from 500 to 2000 of the ratio of the carbon times e raised to the decay constant of carbon times t of dt. So basically what we're doing is we are determining how much ratio of this carbon is lost from 5,000 to 2,000 years. And then for part B, we're going to suppose a body buried in a tomb was determined to have a C14 to C12 ratio of 7.3 times 10 to the negative 13. So approximately how many years old is the body? Okay, so let's start working part A. So for part A, we are just going to evaluate the integral. We have the integral from 500 to 2000, and this ratio constant was 1 times 10 to the negative 12th. Then we have e raised to the negative 0.000121 t dt. Well, if you remember, one of our exponential formulas was if we had an exponential raised to a constant, it is just the integral of that is the exponential function over the constant. So we have 1 times 10 to the negative 12th all over negative 0.000121. Then we have our exponential 0.00121 t, and that is evaluated from 2000 to 500, or from 500 to 2000. So we have 1 times 10 to the negative 12 over negative 0.00121 times e to the negative 0.000121 times 2000 minus e to the negative 0.0000121 times 500. And when you plug all this into a calculator, it gives you a ratio of approximately 1.29 times 10 to the negative 9. So that is how much ratio of C14 to C12 is lost from 500 to 2,000 years. Now for part B, we are going to use our exponential decay function. We had our ratio of C14 to C12 equals our ratio of C14 times e to the negative 0.00121 t. So we know the ratio of the body that was found is this number, 7.3 times 10 to the negative 13th. Then we have a ratio of C14, negative 12, and then e to the negative 0.0000121 t. So for this, we just have to do some basic algebra here to solve this. So we have 7.3 times 10 to the negative 13 over 1 times 10 to the negative 12 equals e to the negative 0.0001 0.21t. Then we have 0.73 equals e to the negative 0.000121t. So now what we are going to do, we're going to take the ln of both sides, and then that will cancel out that exponential and bring its power down, make it a constant. So, or make it its own variable. So we have ln of 0.73 equals negative 0.000121t. And then we have t equals ln of 0.73 over negative 0.000121. And this body is approximately 2,601 years old. So that is it for this course for Calculus 1. Thank you guys so much for watching. I hope you enjoy, and I will reference the textbook that I used for this course if you want to have a textbook reference and just to cite my sources that I used for this course. And I hope this video has been a blessing to you, and I hope that you continue to have a desire to learn whatever it is you're trying to learn. Thank you.